Something growls, invisible, unstoppable, ancient. This is Cygnus X-1, a cosmic enigma that defies expectation and challenges the imagination. It is a black hole that, by all known laws of stellar evolution, should not exist. Born from a star far too massive to leave any remnants behind. Yet here it lingers, a shadow in the cosmic tapestry, devouring light itself. Cloaked in mystery, Cygnus X-1 moves through space like a predator hiding in plain sight, its presence only betrayed by the powerful X-rays it emits. The story begins in 1964, when instruments aboard early rockets first detected flickers of X-ray energy that seemed to come from nowhere. By 1971, the astronomical community was stunned. This was no ordinary celestial object. It orbited a giant blue star, siphoning matter with relentless hunger, a stellar vampire. Its mass, astonishingly large, stretched the limits of theoretical physics. Here was a black hole weighing roughly 15 times the mass of our sun, locked in a gravitational waltz with a luminous supergiant, a dance that churned matter into a swirling, incandescent disk. As the matter spiraled inward, it heated to unimaginable temperatures, releasing torrents of X-rays detectable across thousands of light years. Located approximately 6,000 light years away in the constellation Cygnus, this binary system has captivated astronomers for decades. The blue supergiant dominates visually, but its dense companion, Cygnus X-1 itself, is the true powerhouse. It is one of the first stellar mass black holes ever identified, an extraordinary laboratory for extreme physics. Studying it has illuminated the mechanics of black hole accretion, revealed the effects of gravity in intense conditions, and reshaped our understanding of massive star evolution. The discovery of Cygnus X-1 did not arrive quietly. It sparked controversy. Its extreme properties were so baffling that prominent scientists, including Stephen Hawking, initially wagered against the possibility of it being a black hole. Yet, as observations mounted, skepticism gave way to awe, marking a pivotal moment in astrophysics. The evidence became undeniable. Black holes were not merely theoretical constructs. They were observable, measurable, and capable of reshaping the cosmic landscape. The journey of discovery began with Riccardo Giacconi and his team in 1962. Using instruments aboard a suborbital rocket, they recorded a powerful X-ray source emanating from the constellation Cygnus. This moment marked the birth of X-ray astronomy, opening a new window on the universe. Early observations could only tell scientists that something extraordinarily bright was present. What kind of object could emit such relentless radiation? The answer would emerge slowly over the course of years as data accumulated and theory evolved. Gradually, researchers recognized that they were witnessing a black hole, a celestial object once relegated to the realm of equations and speculation. Cygnus X-1 became a focal point for astronomical research. It provided one of the first strong observational confirmations of black holes predicted decades earlier by Einstein's theory of general relativity. Its presence demanded a reevaluation of stellar life cycles and the fates of the universe's most massive stars. With each observation, each increment of data, astronomers unraveled more of its secrets. High-resolution studies revealed the dynamics of its accretion disk, the violent jets it can produce, and the intricate gravitational interplay with its supergiant companion. The story of Cygnus X-1 is a testament to the gradual, often painstaking nature of scientific discovery. It illustrates how a flicker on a detector can ignite decades of research, debate, and theoretical refinement. It is a tale of patience, of curiosity, and of humanity reaching ever deeper into the cosmos to understand phenomena that once seemed impossible. Even today, Cygnus X-1 remains a beacon for exploration, a reminder of the universe's hidden forces and the enduring mystery of what lies beyond the reach of light. From its initial detection in the early 1960s to the present day, Cygnus X-1 has continually reshaped our understanding of black holes. It has forced astronomers to confront the limits of their models, to test the extremes of physics, and to expand the horizons of human knowledge. This black hole, invisible yet omnipresent, remains a symbol of cosmic power, a silent guardian of secrets in the vast starlit darkness. Its story continues, written in X-rays and gravity waves, a living chronicle of the universe's most extreme and fascinating phenomena. Today, Cygnus X-1 stands as one of the most meticulously studied black holes within our galaxy, a testament to decades of relentless observation, technological innovation, and theoretical refinement. Its journey from a mysterious X-ray source to a confirmed black hole is a saga spanning generations of astronomers and physicists, she left each building upon the discoveries of the last. Cygnus X-1 occupies a unique position in astrophysics, celebrated as the first cosmic object to achieve widespread recognition as a genuine black hole. Discovered in 1964 during a pioneering rocket flight, Cygnus X-1 initially baffled scientists with its extraordinarily intense X-ray emissions. These emissions far exceeded what any ordinary star could produce, prompting researchers to explore exotic explanations. The puzzle began to unravel when astronomers identified that Cygnus X-1 belonged to a binary system. They observed a massive blue supergiant star orbiting an unseen companion. This hidden object, despite possessing only about 15 times the mass of our Sun, wielded a gravitational force so immense that it siphoned material from its luminous partner. As this stolen matter spiraled inward, it heated to extreme temperatures, emitting powerful X-rays before vanishing into the dark heart of the companion. This revelation provided compelling observational evidence for the existence of black holes, long considered purely theoretical constructs. The properties of Cygnus X-1 aligned so closely with predictions for a stellar mass black hole that the global scientific community could no longer dismiss such objects as hypothetical. Even skeptics like Stephen Hawking, who had once wagered against their existence, eventually acknowledged the mounting evidence presented by this extraordinary system. The continued study of Cygnus X-1 has yielded invaluable insights into the mechanics of gravity, the dynamics of accretion, and the extreme physics governing high-energy astrophysical phenomena, establishing it as a crucial laboratory for understanding the universe's most enigmatic processes. The name Cygnus X-1 derives from a combination of its celestial location and the nature of its discovery. Cygnus refers to the constellation in which this object resides. The term is Latin for swan, reflecting the constellation's graceful flight across the night sky. X1 signifies its importance in X-ray astronomy as the first X-ray source detected within Cygnus. At the time of discovery, scientists could only confirm its exceptional brightness in X-rays, leaving the true nature of Cygnus X-1 shrouded in mystery. Later observations identified it as a prime candidate for a black hole, cementing its place in the annals of astrophysics. The naming convention, common in X-ray astronomy, allows subsequent discoveries in the same region to be cataloged systematically as Cygnus X2, Cygnus X3, and so forth, facilitating precise reference and ongoing research across the cosmos. Cygnus X-1's binary system pairs a blue supergiant star with a dense, invisible companion. What distinguishes this companion is its ability to exert an extraordinary gravitational pull, stripping matter from its stellar neighbor to form a superheated accretion disk. As the material spirals inward, it emits intense X-rays, making Cygnus X-1 one of the brightest X-ray sources in the Milky Way. Though the companion's mass is only about 15 times that of our Sun, it is compressed into a volume smaller than a terrestrial city. This combination of immense density and the capacity to trap light within its gravitational field provides compelling evidence of a stellar mass black hole in action. Further examination of Cygnus X-1 has revealed even more astonishing features. The black hole is unusually massive, estimated at around 21 times the mass of our Sun. Conventional models of stellar collapse suggest stars of this size should end their lives as neutron stars rather than black holes, implying that Cygnus X-1 challenges our understanding of stellar evolution and may have formed through atypical processes. Adding to the mystery, the black hole spins at a rate approaching the maximum permitted by Einstein's general theory of relativity, a phenomenon difficult to reconcile with current formation models. These peculiarities have transformed Cygnus X-1 into a cosmic conundrum, driving astronomers to rethink theoretical models and pushing research into the life cycles of massive stars and the formation mechanisms of black holes. The initial discovery of Cygnus X-1 ignited widespread debate and excitement in the scientific community. Astronomers grappled with the challenge of explaining the powerful X-rays emanating from this constellation. Theories ranged from a neutron star to the first observed black hole, and this uncertainty fueled a flurry of research, observations, and global collaboration. Over time, evidence accumulated, tipping consensus toward the recognition of Cygnus X-1 as a bona fide black hole, marking a pivotal moment in astrophysics and providing the first tangible glimpse into phenomena that were once purely theoretical. The Cygnus constellation, prominent in the northern hemisphere, serves as the stage for this remarkable cosmic object. Known as the Swan, Cygnus is easily identifiable by its distinctive cross-like shape, earning it the nickname the Northern Cross. Flying along the Milky Way, the constellation occupies a rich field for stargazing, flanked by Lyra to the west, Draco to the north, Cepheus to the northeast, and Pegasus to the southeast. The brightest star, Deneb, forms part of the summer triangle alongside Vega in Lyra and Altair in Aquila. In mid-northern latitudes, Cygnus is circumpolar, visible year-round but most prominent during summer and early autumn nights. Tracing the Swan begins with Deneb at the tail, extending along its long neck to Alberio at the beak, while the wings stretch horizontally, creating the iconic Northern Cross figure. Throughout history, Cygnus has inspired myths and legends. In Greek mythology, the constellation is linked to Zeus, who transformed into a swan to seduce Leda, queen of Sparta. Another legend connects Cygnus to Orpheus, the fabled musician transformed into a swan after death. Native American interpretations saw it as a bird traversing the Milky Way, representing the soul's journey to the afterlife, while Chinese astronomers envisioned it as a celestial bridge linking star-crossed lovers. These narratives reflect humanity's enduring desire to understand the cosmos through story, blending imagination with the observable universe. Cygnus X-1, residing near the Swan's left wing, continues to fascinate astronomers and stargazers alike. Its gravitational ballet with the blue supergiant star reveals the extreme forces shaping our universe, while its extreme mass, rapid rotation, and intense X-ray emissions offer an unparalleled window into the behavior of matter and energy under the most extraordinary conditions. The ongoing study of Cygnus X-1 has fundamentally advanced our comprehension of black holes, challenged theoretical paradigms, and illuminated the profound mysteries still waiting to be uncovered in the cosmos. Discovered in 1964 during a pioneering rocket flight, Cygnus X-1 emerged as one of the first cosmic X-ray sources ever detected, instantly capturing the attention of astronomers around the globe. Its name carries the letter X for a reason: the extraordinary X-ray emissions it produces, which are the product of an extraordinary cosmic dance. Matter from a massive blue supergiant star is inexorably drawn toward the black hole's immense gravitational pull. As this matter spirals inward, it forms a luminous, swirling accretion disk heated to unimaginable temperatures, unleashing torrents of high-energy X-rays that travel across space, reaching the detectors and observatories here on Earth. This powerful system transforms a distant patch of sky into a natural laboratory, allowing scientists to probe the laws of physics under the most extreme conditions imaginable. The black hole within Cygnus X-1 is estimated to be about 14.5 times the mass of our Sun, placing it among the heaviest stellar black holes known in our galaxy. Located roughly 6,000 light-years away, Cygnus X-1's relative proximity makes it an ideal target for astronomers, who have used it to make groundbreaking observations about black holes, accretion processes, and high-energy astrophysics. Its presence within the rich tapestry of the Cygnus constellation adds a layer of fascination, linking modern scientific discovery with the myths and stories of ancient cultures. To the ancients, this constellation traced the elegant form of a swan gliding across the Milky Way, a celestial image now enriched by the cutting-edge tools of contemporary astronomy. Cygnus itself is a vast and varied constellation, home to a remarkable array of celestial phenomena. The North America Nebula, for instance, stretches across 40 light-years, an immense cloud of glowing ionized hydrogen shaped curiously like the continent it is named after. This nebula, vibrant and photogenic, is a favorite subject for astrophotographers and a striking landmark for those scanning the summer sky. The Veil Nebula, another jewel in Cygnus's stellar crown, represents the lingering aftermath of a titanic supernova that exploded some 8,000 years ago. Its delicate, intricate filaments continue to expand outward, a glowing testament to an ancient cosmic cataclysm and a visible reminder of the life cycles of stars. Cygnus X-1 shares this celestial stage with some of the brightest stars in the night sky. DENM, a blue-white supergiant, shines with the brilliance of more than 50,000 suns, making it not only a central figure in the Cygnus constellation, but also a dominant feature of the Summer Triangle asterism. The diversity of stars within Cygnus is staggering. Some lie relatively close, like Albero at about 400 light-years from Earth, while others, including DENM, are located thousands of light-years away. This enormous spread in distance creates a three-dimensional tapestry that challenges astronomers to map the galaxy with precision and underscores the vast scale of our cosmic neighborhood. Cygnus offers more than visual splendor. It is a key site for understanding stellar evolution. From newborn stars emerging in dense nebular clouds to ancient fading giants, the constellation presents a living chronicle of stellar life cycles. Each object, whether a luminous blue supergiant, a supernova remnant, or a black hole binary system, tells a story of formation, transformation, and destruction. Cygnus X-1 in particular exemplifies the extraordinary extremes that matter and energy can reach in the universe. As matter is drawn from the companion star into the black hole's gravitational grip, it releases energies that dwarf anything achievable on Earth, providing a window into physics that is otherwise inaccessible. For amateur astronomers, locating Cygnus X-1 is an exercise in patience and observation. The constellation is often identified first through the Northern Cross asterism, forming the swan's main body. Danb marks the tip of the swan's tail, and tracing a line from Danb down to Albero, at the swan's beak, guides the eye toward the region where the black hole resides. Though Cygnus X-1 itself remains invisible to the naked eye, its influence is profound, detectable only through the X-rays that travel across thousands of light-years to reach Earth. Cygnus is also home to a number of other astronomical treasures. The Cygnus Loop, also known as the Veil Nebula, offers insights into the life cycles of massive stars and the processes that sculpt the galaxy, while the North America Nebula remains an ever-popular target for both observational and photographic study. Each star and nebula within Cygnus contributes to a cosmic narrative that spans thousands of years, combining myth, observation, and cutting-edge astrophysical research. In this sense, the constellation is not merely a cluster of stars, but a living laboratory where the universe's most profound phenomena, black holes, supernova remnants, star formation, and luminous giants, come into focus, captivating both scientists and stargazers alike, bridging the gap between human imagination and the extreme realities of the cosmos. However, its binary companion, a brilliant blue supergiant star, reveals itself in the night sky to observers armed with a moderately sized telescope. Situated near the left wing of the Swan constellation, about 2/3 of the distance from the star Albero to Etni, which marks the tip of the wing, this luminous companion provides a rare window into a system dominated by one of the universe's most extreme phenomena. For a more precise celestial pinpoint, amateur astronomers can look for a triangular arrangement formed by the stars Eta, Zeta, and Delta Cygni. The companion of Cygnus X-1 resides just inside this triangle, closer to the Zeta side, standing as a beacon in the sky, while its dark partner, the black hole, remains invisible, hidden in the void. Observing this companion allows stargazers to witness firsthand the influence of a cosmic leviathan, one whose gravitational pull warps the surrounding space in profound ways. For the optimal viewing experience, it is essential to choose a night with minimal atmospheric interference and light pollution, allowing the eyes to fully adapt to the darkness. Star charts or advanced astronomy applications can significantly aid in navigating the constellation, guiding explorers to this remarkable binary system, where one star shines and its enigmatic counterpart silently dominates. Black holes, these cosmic enigmas, occupy some of the most mysterious corners of the universe. They are regions in space where gravity reaches unfathomable extremes, so intense that not even light can escape their grasp. This tremendous gravitational force emerges when a massive star collapses at the end of its life cycle, that compressing an astronomical amount of matter into an almost inconceivably small volume. At the core of a black hole lies the singularity, a point of infinite density where conventional physics ceases to apply, and the known laws of the universe collapse into an unknowable state. Surrounding this singularity is the event horizon, often described as the ultimate boundary. Once anything crosses this invisible threshold, it is irreversibly drawn inward, lost forever to the universe outside. Despite the ominous name, black holes are not entirely black. They emit a faint glow, known as Hawking radiation, a subtle phenomenon theorized by the physicist Stephen Hawking. Over incomprehensibly long timescales, this radiation is thought to slowly erode the black hole, causing it to evaporate. While this process has not yet been directly observed, it underscores the delicate interplay between quantum mechanics and gravity at the edge of these cosmic abysses. Black holes manifest in a variety of sizes. Stellar mass black holes arise from the collapse of individual stars, while supermassive black holes reside at the centers of galaxies, including the Milky Way, holding millions or even billions of solar masses within a single invisible point. Each discovery pushes the limits of human understanding and challenges the boundaries of modern astrophysics. The formation of black holes often begins with a stellar cataclysm, a supernova. When a massive star, typically more than 20 times the mass of our Sun, exhausts its nuclear fuel, its core succumbs to gravity, imploding and condensing into a singularity. The resulting gravitational pull is so overwhelming that even photons of light cannot escape, creating the characteristic black void that gives these objects their name. The event horizon marks the outer limit of this gravitational dominion. Within this boundary, the rules of physics as humans comprehend them no longer hold. Matter continues to be compressed relentlessly into the singularity, where density and gravity become infinite. Not all black holes emerge from dying stars. Supermassive black holes at galactic centers grow through complex cosmic processes, such as the merger of smaller black holes and the gradual accumulation of gas and dust over billions of years. Theoretical models also propose the existence of primordial black holes, formed under extreme conditions in the infant universe shortly after the Big Bang. While still hypothetical, these ancient objects could offer profound insights into the formation and evolution of the cosmos itself. Black holes exist across a vast spectrum of sizes. Stellar black holes, born from collapsing stars, typically range from 5 to several dozen times the mass of our Sun. Intermediate mass black holes, which are much harder to detect, may weigh from 100 to 100,000 solar masses. At the opposite extreme are supermassive black holes, residing at the centers of galaxies and containing millions or even billions of solar masses. The smallest theorized black holes, possibly originating in the early universe, could be as tiny as a single atom while containing the mass of a large mountain, making them nearly impossible to detect. Rotating black holes, also known as Kerr black holes, introduce another layer of complexity. Their rapid spin drags the very fabric of space-time around them, a phenomenon called frame dragging, which profoundly affects nearby matter and energy, and might even allow the extraction of rotational energy from the black hole itself. The event horizon, defining the point of no return, remains one of the most mysterious aspects of these objects. Once crossed, matter and light are inexorably drawn inward toward the singularity, a point of unimaginable density. Photons bend and twist as they near the horizon, and those that pass beyond are trapped forever, spiraling into oblivion. The journey of matter into a black hole involves extreme deformation known as spaghettification, stretching and compressing objects due to the differential gravitational forces across them. Even the most fundamental particles are eventually torn apart as they approach the singularity. Time itself behaves in bizarre ways in proximity to a black hole. For a distant observer, time slows dramatically for objects approaching the event horizon, eventually appearing to freeze at the threshold. From the perspective of the falling object, however, time continues normally, creating a paradox that challenges our understanding of space and time. Gravitational time dilation, spaghettification, and the one-way nature of the event horizon together paint a picture of black holes as both destructive and awe-inspiring, testing the limits of physics and imagination. Each of these features, from the luminous companion star to the invisible singularity, forms a tapestry of cosmic wonder, illustrating the delicate interplay between light and darkness, gravity and time at the very edges of our universe. However, for the object in free fall toward the black hole, time would feel ordinary, ticking away just as it always does, highlighting the profound and relative nature of time when confronted with such extreme gravitational forces. Black holes, these enigmatic giants of the cosmos, are invisible to our eyes, yet scientists have devised remarkably clever methods to uncover their presence and reveal their secrets. One primary strategy is to observe the influence they exert on the surrounding environment. As matter spirals toward a black hole, it forms an incandescent, spinning disk of gas and dust known as an accretion disk. The temperatures in this swirling maelstrom soar to unimaginable extremes, causing the material to emit torrents of X-rays that space telescopes can detect, painting an indirect picture of the invisible monster at the center. Beyond the fiery disk, the gravitational grip of a black hole tugs relentlessly on nearby stars. By meticulously tracking the orbits of stars in the dense core of our galaxy, astronomers have inferred the presence of a supermassive black hole at the heart of the Milky Way. The star's erratic paths and blistering velocities betray the unseen mass lurking at the center, a celestial puppeteer manipulating its stellar companions with invisible strings. Another revolutionary method involves gravitational waves, ripples in space-time first predicted by Einstein. When two black holes collide in a violent cosmic dance, these waves radiate outward, reaching detectors on Earth and offering precious information about the masses, spins, and dynamics of the colliding giants. In a historic breakthrough, humanity captured the first image of a black hole using a coordinated global network of radio telescopes. This stunning image revealed the shadow cast by the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational clutch. These indirect glimpses and observations continue to peel back layers of mystery, transforming black holes from mere theoretical oddities into tangible objects of scientific inquiry. Hawking radiation, a theoretical phenomenon predicted by physicist Stephen Hawking, adds yet another layer to our understanding. According to his revolutionary insight, the intense gravitational field near a black hole's event horizon generates quantum fluctuations that produce particle-antiparticle pairs. Occasionally, one particle falls into the black hole while its counterpart escapes, appearing to the outside world as radiation emitted by the black hole itself. Over time, this process gradually diminishes the mass and energy of the black hole. While the effect is imperceptibly slow for colossal black holes, smaller ones could evaporate entirely. This concept bridges the enigmatic realms of quantum mechanics and general relativity, two pillars of modern physics that have long resisted unification, suggesting tantalizing possibilities for the ultimate fate of black holes and the universe itself. Black holes warp space and time with staggering intensity, creating gravitational wells that distort everything around them. Imagine space-time as a stretched rubber sheet. A black hole would be a dense bowling ball pressing into this sheet, producing a deep depression that curves the surrounding region. This curvature alters the flow of time for objects nearby, creating time dilation, which slows time from the perspective of a distant observer. The closer an object approaches the event horizon, the more extreme this effect becomes, until it reaches a point of no return. Light, too, succumbs to the warping of space-time, bending around the black hole or becoming trapped in orbit, forming what is known as a photon sphere. This bending can produce gravitational lensing, a natural magnification that distorts and amplifies light from distant stars and galaxies, allowing astronomers to probe the cosmos in extraordinary ways. At the very core of a black hole lies the singularity, the most baffling and extreme phenomenon in the universe. Here, conventional physics breaks down and the rules governing space and time collapse. The singularity is believed to harbor infinite density, compressing all the black hole's mass into a single point of zero volume. The gravitational pull is so overwhelming that nothing can escape, not even light, and the equations used to describe space-time yield infinite values, signaling the limits of our current understanding. Physicists speculate that new theories, potentially involving quantum gravity, will be necessary to explain what occurs in this extreme environment. The singularity challenges the very foundations of reality, representing the ultimate frontier of human knowledge. Cygnus X-1, one of the most studied black holes in our galaxy, exemplifies the phenomena of stellar mass black holes. Estimated to be 15 times the mass of the Sun, Cygnus X-1 remains small in size compared to supermassive black holes, yet massive enough to wield tremendous gravitational influence. Astronomers have determined its mass by observing the dynamics of its companion star, a blue supergiant that orbits the black hole every 5.5 days. This precise orbital ballet allows for accurate calculations of the black hole's mass, situating Cygnus X-1 at the upper limits of stellar mass black holes and offering a window into the processes that govern the death of massive stars. Though a titan within its category, Cygnus X-1 is dwarfed by the behemoths at galactic centers. Supermassive black holes, millions or even billions of times more massive than the Sun, render Cygnus X-1 a mere cosmic pebble in comparison. Sagittarius A star, the colossal black hole at the center of the Milky Way, possesses a mass roughly 4 million times that of the Sun, exceeding Cygnus X-1's mass by more than 260,000 times. Yet the study of Cygnus X-1 remains invaluable, illuminating the life cycles of massive stars and offering insights into the formation and evolution of black holes, from stellar remnants to the gargantuan rulers of galactic cores. The story of black holes is one of extremes of gravity, density, and mystery. From the faint whispers of Hawking radiation to the violent collisions that ripple space-time, these cosmic enigmas reveal the universe's hidden forces. They challenge our understanding of reality, bend the fabric of space and time, and confront us with singularities where the known laws of physics falter. Yet, through ingenious observation and relentless curiosity, humanity continues to unravel their secrets, one gravitational ripple, one orbiting star, one captured shadow at a time. However, when set against the broader landscape of stellar mass black holes, Cygnus X-1 stands out as an unusually large specimen. Most black holes born from collapsing stars weigh in at roughly 5 to 10 times the mass of our Sun, yet Cygnus X-1 pushes a staggering 15 solar masses, placing it firmly at the upper limit of the stellar mass black hole category. Beyond these stellar giants lies the elusive class of intermediate mass black holes, bridging the gap between stellar mass and supermassive titans. These rare objects, ranging from hundreds to hundreds of thousands of solar masses, are infrequently observed, their scarcity highlighting the vast range of scales across black holes in our universe. Even so, Cygnus X-1, while formidable, is still dwarfed by these intermediate leviathans, emphasizing the staggering diversity in cosmic scales. Cygnus X-1 is not just massive, it is also a marvel of motion, spinning at a rate almost incomprehensible. Its stellar remnant rotates at nearly half the speed of light, with its equator hurtling through space at approximately 150 million meters per second. This phenomenal velocity arises from the collapse of its progenitor star and the conservation of angular momentum, a cosmic law that ensures the rotation of a parent star is inherited and amplified in its black hole offspring. This extreme rotation is far from a trivial detail. It has profound effects on the surrounding environment, creating a dramatic gravitational phenomenon known as frame dragging. In this process, the very fabric of space-time is twisted and pulled along by the black hole's rotation, reshaping the motion of matter and light nearby, and intensifying the extreme conditions that define the black hole's vicinity. Astronomers measure the spin of black holes like Cygnus X-1 by observing X-ray emissions from the accretion disk, a whirling maelstrom of matter spiraling inward. The patterns, intensities, and subtle shifts in these X-rays reveal crucial information about the black hole's properties, including the precise rate of its rotation. Each observation turns Cygnus X-1 into a cosmic laboratory, a natural setting where scientists can study the interplay of extreme gravity, test the predictions of Einstein's general relativity, and witness conditions impossible to recreate on Earth. This black hole spins at an almost mind-boggling pace, completing close to 1,000 rotations every second. Its rotation drags space-time itself, creating a vortex that influences the motion of nearby objects and even warps the path of light. The rotation also amplifies Cygnus X-1's magnetic field, which interacts intensely with the surrounding accretion disk. This interaction produces colossal jets of particles launched from the black hole's poles at velocities approaching the speed of light. These jets extend thousands of light years, shaping the interstellar medium far beyond the immediate vicinity of the black hole. Additionally, the rapid spin draws the innermost, stable circular orbit closer to the event horizon, allowing matter to approach more closely before plunging in. This proximity enhances the efficiency with which energy is extracted from infalling material and influences the characteristics of gravitational waves emitted during black hole mergers, providing astronomers with essential clues about these enigmatic objects and the structure of space-time around them. Frame dragging, a prediction of Einstein's theory, is vividly illustrated by Cygnus X-1. This effect occurs when a massive, rotating object twists the surrounding space-time, akin to a spinning ball dragging water around it, creating a vortex. In Cygnus X-1's binary system, a blue supergiant orbits the black hole, losing material to its gravitational pull. The black hole's rotation drags space-time, causing the inner regions of the accretion disk to spin faster than they otherwise would. This extra rotation modifies the X-ray emissions, allowing scientists to precisely calculate the black hole's spin, which is nearly the maximum allowed by general relativity. Observing frame dragging in Cygnus X-1 not only confirms theoretical predictions, but also offers an unparalleled view into how matter and energy behave in extreme gravitational environments, highlighting the intimate connection between rotation, gravity, and the universe's structure. Cosmically speaking, Cygnus X-1 is young, estimated at around 6 million years old, a mere infant compared to many other galactic structures. Its age has been determined through detailed observations of its companion star and the surrounding stellar environment. This youth helps explain its vigorous activity. The black hole continues to consume material from its companion star, generating intense X-rays and relativistic jets. Studying such a young, energetic black hole provides valuable insights into the early evolution of black holes and their influence on surrounding space, helping astronomers reconstruct the life cycles of massive stars and the timeline of our galaxy's formation. Located approximately 6,000 light-years from Earth, Cygnus X-1's binary system presents an ideal laboratory for studying extreme gravitational phenomena. Its accretion disk, a swirling, flattened collection of gas and dust, forms as material drawn from the blue supergiant star spirals inward rather than falling straight in. Friction and compression heat the disk to extraordinary temperatures, producing intense X-rays detectable from Earth. This luminous disk acts as a cosmic spotlight, revealing the otherwise invisible black hole and providing data on its mass, spin, and dynamic behavior. Observations of the accretion disk allow scientists to measure the black hole's spin, study how matter behaves under intense gravitational forces, and test fundamental principles of physics in a natural setting that cannot be replicated in laboratories. Cygnus X-1's accretion disk, its rapid rotation, and its gravitational influence together form a spectacular cosmic system, one where energy, matter, and spacetime interact in a vivid, ongoing dance. The black hole's presence transforms its surroundings, producing phenomena that stretch across thousands of light years, from swirling disks and X-ray emissions to relativistic jets and gravitational wave signatures. Each observation peels back another layer of mystery, turning Cygnus X-1 into one of the most fascinating subjects for understanding the universe's most extreme environments and the fundamental forces that govern them. Furthermore, the behavior of the accretion disk surrounding Cygnus X-1 provides a remarkable confirmation of the predictions of general relativity. In this extreme cosmic environment, the interplay of light and matter near the black hole's event horizon becomes a natural laboratory for testing Einstein's theories under conditions that are impossible to replicate on Earth. Observing the distortions of spacetime and the warping of light in this region allows scientists to probe the very fabric of the universe, deepening our understanding of fundamental physics and revealing the intricate structure of spacetime itself. Cygnus X-1's companion star, HDE2 268068-8, is a blue supergiant of extraordinary scale and intensity. Weighing in at roughly 40 times the mass of our Sun, it radiates with a surface temperature of approximately 30,000 Kelvin, making it one of the hottest and most luminous stars known to astronomers. This celestial giant orbits the black hole at the center of Cygnus X-1 in a tight, dramatic embrace, completing a full orbit every 5.5 days. This close gravitational dance subjects the star to relentless tidal forces, gradually stripping away its outer layers. These expelled layers spiral toward the black hole, forming a searing accretion disk of gas and dust that heats to millions of degrees, emitting powerful X-rays that first signaled the existence of Cygnus X-1. This discovery marked one of the earliest identifications of a black hole, cementing the system as a cornerstone in the study of extreme astrophysics. The ongoing interaction between Cygnus X-1 and its blue super companion is a cosmic ballet of staggering proportions. As the black hole's immense gravitational pull strips stellar material from the companion, this matter forms a swirling, spiraling disk around the black hole. Within this disk, friction and compression propel temperatures to millions of degrees, generating intense radiation across the entire electromagnetic spectrum, from radio waves to X-rays. The luminous output of this binary system is so extraordinary that at times it can rival or even surpass the brightness of entire galaxies. Not all material succumbs to the black hole's pull. Some is violently expelled in the form of relativistic jets that extend thousands of light years into space. These jets interact with the surrounding interstellar medium, potentially triggering the birth of new stars in distant regions and shaping the cosmic environment on a grand scale. Over time, the continuous siphoning of matter can transform the companion star, shrinking it into a denser object, or in extreme cases, leading to its complete consumption by the black hole. This process illustrates the profound influence that black holes exert on their stellar neighbors and highlights the intricate, transformative power of gravitational interactions in the universe. The binary system's orbital period, approximately 78 years, illustrates the vast spatial scale and the formidable gravitational forces at play. A single revolution around the common center of mass takes nearly 8 decades, reflecting the delicate balance between distance and gravitational dominance. Binary star systems are ubiquitous in our galaxy, with estimates suggesting that more than half of all stars exist in such multi-star arrangements. Orbital periods vary dramatically, ranging from mere hours for close binaries to thousands of years for widely separated pairs. In the case of this system, the 78-year orbit positions the stars at a moderate separation, enabling detailed study of both objects individually. Such observations provide invaluable insights into stellar evolution, mass transfer, and the complex gravitational choreography that governs binary systems. By tracking these stars over multiple orbits, astronomers have been able to measure their masses, sizes, and evolutionary stages with extraordinary precision, contributing to a broader understanding of the life cycles of stars throughout the cosmos. Cygnus X-1's binary nature defines much of its behavior and observable characteristics. The gravitational pull of the black hole strips the outer layers of the blue supergiant, feeding a persistent accretion disk of superheated gas and dust. As material spirals inward, it emits intense X-rays, making Cygnus X-1 one of the brightest X-ray sources in our galaxy. The system also produces high-velocity particle jets that emanate nearly at the speed of light, a visual testament to the immense forces at work. The orbital motion of the stars introduces periodic fluctuations in X-ray emissions. When the supergiant passes in front of the disk, it partially eclipses the X-ray source, providing astronomers with a unique tool to map the geometry of the system and probe the physical properties of both the black hole and its stellar companion. This interaction serves as a natural laboratory for extreme physics, offering a window into matter behavior under intense gravitational stress, stellar evolution under mass transfer, and the mechanisms by which black holes grow and influence their surroundings. Binary star systems offer an extraordinary glimpse into stellar evolution, allowing astronomers to study two stars born at the same time, but with differing masses and compositions. In this system, the more massive star has already evolved into a red giant, expanding dramatically as it exhausts hydrogen fuel at its core, while its smaller companion continues to fuse hydrogen steadily, remaining on the main sequence. This juxtaposition of evolutionary stages provides scientists with a living laboratory for testing models of stellar aging, demonstrating how mass and chemical composition influence the pace and nature of a star's life cycle. Observing this binary system also allows for precise determination of key stellar parameters such as mass, radius, and surface temperature, which are essential for understanding the internal dynamics and life cycles of stars. The relationship between Cygnus X-1 and its companion star exemplifies the interplay of gravity, radiation, and matter on cosmic scales. Each orbit and each transfer of mass illuminate the extreme conditions under which stars and black holes exist. The system reveals the transformative potential of gravity, where the very existence of one object shapes the fate of another, and where radiation and jets sculpt the surrounding galaxy. It stands as a testament to the power and elegance of celestial mechanics, a vivid illustration of the forces that govern the universe, and a continuing source of knowledge about some of the most extreme and fascinating phenomena known to science. Furthermore, this binary system provides a window into the future stages of stellar evolution, revealing a cosmic dance of destruction and creation. As the larger star in the pair continues to expand, it may one day engulf its smaller companion, plunging the system into a dramatic common envelope phase. In some cases, this intimate encounter can culminate in a merger, forging a singular, extraordinary stellar object. These events are not merely spectacular, they also have far-reaching consequences for the cosmos. When such a merger or engulfment occurs, the violent interactions can trigger supernova explosions, scattering heavy elements into the surrounding space. These elements, forged in the crucible of dying stars, are essential building blocks for planets, and ultimately, for life itself. In this intricate gravitational ballet, the interaction between a companion star and a black hole becomes a captivating process of cosmic mechanics. The black hole, with immense gravitational pull, begins to siphon material from the companion star as they orbit each other in tight proximity. The stripped material does not plunge directly into the black hole, but instead forms a luminous, swirling accretion disk composed of gas and dust. This transformation begins as the companion star enters its red giant phase, expanding beyond its Roche lobe, the zone where its gravitational dominance ends. The star's outer layers succumb to the black hole's relentless pull, spiraling inward. As this stellar matter flows toward the black hole, friction and compression heat it to extraordinary temperatures, often reaching millions of degrees. This superheated plasma emits intense radiation, predominantly in the form of X-rays, rendering these binary systems among the brightest X-ray sources in the observable universe. Yet not all material is captured. Some is ejected in powerful, focused jets perpendicular to the accretion disk, while other portions are swept away by radiation pressure. This ongoing interplay of gravity, matter, and energy creates a dynamic, ever-changing system that continues to mesmerize astronomers. Gravity is the invisible choreographer orchestrating the relationship between Cygnus X-1 and its blue supergiant companion. The black hole, with a mass roughly 15 times that of our Sun, dominates the system, distorting the shape of its partner and drawing stellar material into the surrounding accretion disk. This process, called accretion, unleashes extraordinary energy as matter spirals inward, heating to extreme temperatures and emitting powerful X-rays detectable from Earth. The gravitational forces also dictate the binary system's orbital rhythm, completing a full orbit approximately every 5.5 days. The combination of orbital speed and companion mass enables scientists to determine the black hole's mass and confirm its identity. Over time, tidal forces reshape the orbit and influence the rate of material transfer, showcasing the ever-evolving and dynamic nature of this cosmic partnership. X-rays emitted from Cygnus X-1 are the signature of its binary nature, revealing the violent interplay between a massive blue supergiant and its dense black hole companion. The accretion disk around the black hole heats to extreme temperatures as matter spirals inward, producing X-rays and high-energy radiation. Some of the inflowing matter is expelled in relativistic jets, where particles accelerated near light speed interact with magnetic fields, further amplifying the system's X-ray brightness. The story of cosmic X-ray discovery began in the early 1960s, at the dawn of the space age. Scientists launched high-altitude rockets carrying specialized detectors designed to capture radiation blocked by Earth's atmosphere. In 1962, Ricardo Hakonet's team recorded a strong X-ray signal from the constellation Scorpius, a discovery that marked the birth of X-ray astronomy. Initially mistaken for reflected solar X-rays from the moon, further observations revealed distant, immensely energetic sources beyond the solar system. This revelation transformed astronomical study, unveiling objects and phenomena invisible to optical telescopes, including neutron stars, black holes, and superheated galactic gas, and ushering in the era of multi-wavelength astronomy. X-ray emissions from Cygnus X-1 continue to illuminate its nature, confirming it as a binary system composed of a blue supergiant star and a stellar mass black hole. The X-rays originate from the intense interactions near the black hole's event horizon, where matter from the companion star forms a hot, spiraling accretion disk. By analyzing the patterns, intensity, and spectrum of these X-rays, astronomers gain critical insights into the black hole's size, spin, and its influence on surrounding matter. This ongoing observation not only reveals the hidden dynamics of Cygnus X-1, but also expands our understanding of the powerful forces that shape the cosmos. Furthermore, X-ray observations of Cygnus X-1 have uncovered a mesmerizing tapestry of brightness fluctuations, ranging from fleeting milliseconds to extended periods spanning days. Each variation acts like a whisper from the depths of space, revealing the tumultuous activity occurring perilously close to the event horizon, the invisible boundary beyond which nothing can escape a black hole's gravitational grip. By meticulously decoding these X-ray signals, scientists are able to probe the very fabric of space-time, testing the predictions of general relativity while deepening our understanding of matter under the most extreme conditions imaginable. Cygnus X-1's X-ray output has been pivotal in shaping the broader field of black hole research. As one of the earliest discovered and most intensively studied black hole systems, its X-ray data has become a cornerstone for astronomers and astrophysicists, offering a rare glimpse into the inner workings of these enigmatic cosmic giants. Specialized X-ray telescopes and detectors, often perched aboard satellites orbiting far above Earth's atmosphere, serve as the primary tools for capturing these elusive signals. Earth's atmosphere, dense enough to block incoming X-rays, necessitates placing instruments in space to achieve precise measurements. Among these observatories, NASA's Chandra X-ray Observatory, launched in 1999, stands out for its ability to focus X-rays with exquisitely polished mirrors onto advanced detectors. These detectors measure not only the energy but also the timing and position of individual X-ray photons, creating detailed images and spectra that reveal the secrets of the universe. Complementary missions such as XMM Newton and New Star provide additional perspectives, allowing scientists to combine data from multiple sources to construct a more comprehensive view of X-ray emitting phenomena. Through sophisticated computer modeling and statistical analysis, researchers extract essential information about the temperature, density, composition, motion, and evolution of these high-energy objects. By studying Cygnus X-1, scientists gain invaluable insights into some of the universe's most energetic and extreme environments. Its X-ray variability illuminates the nature of black holes and their interaction with surrounding matter. The system is a binary consisting of a luminous blue supergiant star orbiting a compact companion that has been identified as a stellar mass black hole. The rapid fluctuations in X-ray brightness, occurring on timescales as brief as milliseconds, reveal that the region producing these high-energy photons must be extraordinarily compact, consistent with the presence of a black hole. These fluctuations originate from the inner accretion disk, where matter spirals inward at tremendous velocities before succumbing to the black hole's gravity. The patterns of variability also provide crucial clues about the geometry of the accretion flow and the processes by which energy is liberated. Such studies illuminate how black holes feed, how they generate powerful jets of particles that can span thousands of light years, and how they influence their cosmic neighborhoods. Cygnus X-1 is among the brightest X-ray sources in our galaxy, producing a luminosity that can reach tens of thousands of times that of our Sun in the X-ray spectrum alone. Unlike other cosmic X-ray sources, such as supernova remnants or galaxy clusters, which emit more steadily, Cygnus X-1 exhibits rapid and complex variability. Its spectrum contains both soft and hard X-rays, with the balance shifting over time, offering scientists a dynamic laboratory to explore the physics of matter under extreme gravitational stress. The point-like nature of its X-ray emissions, concentrated around a compact region near the black hole, makes Cygnus X-1 an unparalleled site for studying phenomena that cannot be replicated on Earth. The study of black hole emissions has revolutionized astrophysics, revealing the extraordinary behaviors of these cosmic enigmas. Observations of radiation and particle jets from the vicinity of black holes have led to landmark discoveries, including strong evidence for Hawking radiation, the faint glow predicted by Stephen Hawking that suggests black holes slowly emit particles over time. While direct detection of this radiation from distant black holes remains beyond current capabilities, laboratory analogs have provided compelling support for its existence. Furthermore, X-ray studies of accretion disks have shed light on the spin, mass, and dynamics of black holes, offering stringent tests for general relativity in the most extreme gravitational environments. The detection of gravitational waves from colliding black holes has added a new dimension, confirming Einstein's predictions while inaugurating a revolutionary era of observational astronomy. The first image of a black hole shadow captured by the Event Horizon Telescope has provided visual proof of the event horizon, allowing direct study of matter and energy at the precipice of a black hole, and offering unprecedented opportunities to test theories of gravity and spacetime. Cygnus X-1 remains a cosmic enigma that has expanded the boundaries of our understanding of stellar evolution. Discovered in 1964, this powerful X-ray source is now known to be a binary system comprised of a blue supergiant star and a compact companion of extraordinary density. The companion's immense gravitational pull strips matter from the supergiant, forming a luminous accretion disk that radiates intense X-rays. Its mass, estimated at about 14.5 times that of our Sun, far exceeds the theoretical limit for a neutron star, leading to the groundbreaking realization that Cygnus X-1 harbors one of the first identified stellar mass black holes. This discovery compelled astrophysicists to reconsider models of stellar death, raising questions about how massive stars collapse directly into black holes rather than exploding as supernovae. Cygnus X-1 has therefore become an essential laboratory for exploring the extreme physics of black holes, the violent end stages of massive stars, and the extraordinary conditions under which matter behaves at the edge of the cosmos. Moreover, the discovery and continued observation of Cygnus X-1 have transformed the way astronomers think about the universe, reaching far beyond the confines of a single stellar system. This enigmatic black hole has become a focal point in understanding the intricate dance of gravitational waves, the evolution of galaxies, and the vast, often invisible distribution of matter that permeates the cosmos. Every new observation challenges long-held assumptions, refining the models that describe how the universe's most massive stars live and ultimately die. Cygnus X-1, one of the most famous black holes within our Milky Way galaxy, has captivated scientists since its initial discovery, acting as both a beacon and a puzzle in astrophysics. Current theories indicate that this cosmic titan emerged from the dramatic collapse of a massive star bound in a binary system, a process thought to have unfolded approximately 6 million years ago. Its progenitor star, estimated to be about 40 times the mass of our Sun, exhausted its nuclear fuel, triggering a chain of events that would leave a mark on cosmic history. As the core of the star imploded, a supernova explosion ensued, but unlike typical supernova, this event was unusually weak. Instead of violently dispersing the star's mass into space, most of it fell back onto the collapsing core, forming the black hole we observe today. The star's companion, a resilient blue supergiant, survived this cataclysm and continues its orbit, providing a steady stream of material that fuels the black hole. This ongoing interaction generates powerful X-ray emissions, which were instrumental in Cygnus X-1's initial detection. Recent research has revealed that the black hole spins at an astonishing rate, approaching the theoretical maximum allowed by Einstein's general relativity. This extreme rotation offers critical clues about how the black hole formed and the internal distribution of matter in its progenitor star prior to collapse. Weighing roughly 21 times the mass of our Sun, Cygnus X-1 ranks among the most massive stellar black holes ever discovered, posing a serious challenge to conventional models of stellar evolution. According to current astrophysical understanding, stars massive enough to produce black holes of this scale should shed substantial mass before collapsing due to powerful stellar winds and intense pulsations during their final evolutionary stages. These processes were thought to limit the mass of the resulting black hole to around 15 times the mass of the Sun. Yet Cygnus X-1 defies these predictions. This discrepancy has prompted scientists to explore alternative formation scenarios, such as the possibility that the progenitor star formed through the merger of two massive stars, allowing it to retain more mass, or that it developed in a low metallicity environment, where weaker stellar winds would reduce mass loss. The existence of Cygnus X-1 has sparked a surge of research into these massive stellar black holes, providing a window into the life cycles of the universe's most extraordinary stars. Metallicity, the abundance of elements heavier than helium within a star, plays a crucial role in determining stellar evolution and black hole formation. Stars with low metallicity face less resistance to radiation, allowing them to grow larger and retain more mass, increasing the likelihood of forming massive black holes directly. Conversely, high metallicity stars lose significant mass through strong stellar winds, often resulting in smaller black holes or neutron stars after supernovae. This interplay between metallicity and stellar evolution has broad implications, shaping our understanding of gravitational wave events and the distribution of black hole masses across cosmic history. As the universe has gradually enriched in metals over billions of years, the typical masses of newly formed black holes may have shifted, altering the kinds of mergers we detect today. Cygnus X-1, situated in the constellation Cygnus, exemplifies the complex nature of stellar evolution in binary systems. The blue supergiant companion continues to orbit the black hole, illustrating how interactions between stars can significantly influence their evolution. The presence of a black hole in this relatively young system indicates that stellar collapse can occur more rapidly than previously assumed, challenging traditional timelines for massive stars to exhaust their nuclear fuel. It also highlights the need to study binary and multiple star systems in detail, as these interactions can be pivotal in forming exotic objects such as black holes. Beyond its immediate environment, Cygnus X-1 has profound implications for understanding galaxy formation. Its presence within the Milky Way supports the idea that black holes are widespread across the universe. This realization strengthens theories suggesting that supermassive black holes, millions or even billions of times the mass of Cygnus X-1, play a central role in shaping galaxies. These cosmic giants occupy the centers of most large galaxies, their growth intimately linked with the evolution of their host galaxies. As galaxies accumulate mass, their central black holes grow by accreting surrounding matter, releasing energy that can regulate star formation. This feedback mechanism explains the observed correlation between a galaxy's mass and that of its central black hole, revealing a symbiotic relationship that has influenced cosmic evolution for billions of years. Cygnus X-1 continues to be a focal point for astronomers and astrophysicists, offering insights into the life cycles of massive stars, the physics of black hole formation, and the dynamic evolution of galaxies. Its existence forces us to rethink fundamental aspects of stellar life, challenges the limits of our theoretical models, and serves as a reminder of the intricate and often surprising mechanics that govern the universe. Each new discovery surrounding Cygnus X-1 brings us closer to unraveling the mysteries of cosmic formation, illustrating the extraordinary power, complexity, and beauty of the universe in which we reside. Furthermore, the meticulous investigation of Cygnus X-1 and analogous celestial phenomena has profoundly expanded our comprehension of matter under the influence of extreme gravitational forces. This expanding body of knowledge plays a pivotal role in shaping theoretical models that describe how gas and dust are drawn toward supermassive black holes in the nascent stages of the universe, offering compelling explanations for the astonishingly rapid growth of both black holes and galaxies during the cosmic dawn. As astronomers continue to observe Cygnus X-1 alongside its cosmic counterparts, they steadily refine the predictive frameworks of galaxy formation, gradually constructing a more precise and detailed map of the universe's complex landscape. Cygnus X-1 emerges as a singularly extraordinary celestial entity, one that challenges and stretches the frontiers of our understanding regarding stellar evolution and black hole genesis. At the heart of this system lies a colossal blue supergiant star, locked in a gravitational ballet with a dense, unseen companion that has been conclusively identified as a stellar mass black hole. Estimates place the mass of this black hole at approximately 15 times that of our Sun, a figure that exceeds the predictions of conventional stellar evolution models for the ultimate fate of massive stars. This unexpected measurement calls into question previously held assumptions regarding the upper limits of stellar mass and the mechanisms governing black hole formation. Traditional astrophysical theory suggested that stars above a certain mass threshold would shed most of their material through intense stellar winds long before collapsing into black holes. However, the existence of Cygnus X-1 demonstrates that some stars can retain a far greater proportion of their mass throughout their lifetimes, ultimately enabling the creation of more massive black holes than previously anticipated. This revelation carries profound implications for our understanding of stellar life cycles, the distribution of black hole populations, and even the gravitational waves emitted from black hole mergers. Cygnus X-1 functions as a natural laboratory of the cosmos, compelling scientists to continually update their theoretical models and expand the boundaries of knowledge regarding the most massive and enigmatic objects in the universe. Astronomers employ a diverse suite of telescopes to study Cygnus X-1, each instrument designed to capture distinct wavelengths of electromagnetic radiation emitted by this captivating cosmic system. Radio telescopes, with their immense dish antennas often configured into precise arrays, detect the low-energy radio waves emitted from the system, furnishing crucial information about its structural intricacies and dynamic behavior. These instruments have revealed the existence of relativistic jets of matter expelled from the black hole at near light speeds, composed of highly charged particles that emit detectable radio signals. Detailed radio observations have also allowed scientists to probe the dimensions, density, and temperature of the accretion disk, the superheated swirl of gas spiraling inexorably into the black hole, offering critical insights into the energetic processes driving this cosmic powerhouse. By synthesizing radio data with observations across the electromagnetic spectrum, astronomers have confirmed the presence of a black hole in Cygnus X-1, producing precise measurements of both its mass and rotational dynamics. Optical telescopes, both terrestrial and space-based, provide complementary insights by observing Cygnus X-1 in visible light. While the black hole remains invisible to direct observation, these instruments reveal the characteristics of its luminous companion star and the surrounding gas and dust. Notably, the Hubble Space Telescope has contributed substantially to our understanding, capturing the interplay between the stellar giant and its gravitationally dominant partner. X-ray telescopes are indispensable for probing Cygnus X-1, as black holes are prolific sources of high-energy X-ray radiation. Observatories such as the Chandra X-ray Observatory and XMM Newton furnish high-resolution images and spectra, enabling scientists to investigate the searingly hot gas swirling near the event horizon and to quantify the intensity of the gravitational forces at play. These observations provide a window into the extreme physics governing matter in such intense gravitational fields, revealing temperatures, compositions, and dynamic interactions that were previously beyond reach. Gamma-ray telescopes, including the Fermi Gamma-ray Space Telescope, capture the highest energy emissions from Cygnus X-1, shedding light on the most violent and energetic phenomena within the system, such as particle acceleration within the jets and interactions between the black hole and its stellar companion. Radio telescopes have been particularly instrumental in unraveling the mysteries of Cygnus X-1, offering unprecedented detail about the behavior and structure of this cosmic engine. They have allowed astronomers to map the colossal jets of plasma streaming from the black hole, to analyze the movement and density of the accretion disk, and to understand the mechanisms generating the tremendous energy output of the system. This multifaceted approach Integrating data from radio, optical, X-ray, and gamma-ray observations has enabled the creation of a holistic model of Cygnus X-1, establishing it as one of the most thoroughly studied black hole systems in our galaxy. Space-based observatories have revolutionized the study of Cygnus X-1 by bypassing atmospheric interference and providing unparalleled access to high-energy phenomena. Operating beyond Earth's protective envelope, these instruments monitor the system's X-ray and gamma-ray emissions, revealing the behavior of matter as it spirals into the black hole and forms a luminous accretion disk. Observatories like Chandra and the retired Compton Gamma Ray Observatory have supplied detailed spectral and temporal data clarifying the energy distribution and variability of Cygnus X-1. Continuous monitoring from these orbital platforms enables scientists to observe the evolution of the system over time, capturing subtle shifts in behavior and offering critical insights into the physics of black holes. Multi-wavelength observation strategies, spanning from radio waves to gamma rays, construct a comprehensive narrative of the complex interactions and processes within this binary system, significantly advancing our grasp of the universe's most extreme objects. The Chandra X-ray Observatory, in particular, has been instrumental in deepening our knowledge of Cygnus X-1, delivering unprecedented clarity and resolution in the X-ray spectrum. Its high-resolution imaging has allowed astronomers to scrutinize the inflow of matter from the companion star, measuring the black hole's spin with remarkable precision, a key parameter in understanding its evolution and energetic behavior. Chandra's contributions have unveiled phenomena that were once hidden, transforming Cygnus X-1 from a theoretical curiosity into a well-characterized laboratory for exploring the physics of stellar mass black holes and their interactions with companion stars. Furthermore, Chandra has opened an extraordinary window into the universe, allowing researchers to probe the powerful jets of matter violently ejected from the regions surrounding the black hole. These streams of high-energy particles traveling at nearly the speed of light interact in complex ways with the surrounding space, creating shock waves and turbulence that ripple through the cosmos. By capturing these emissions in exquisite detail, astronomers have been able to map how the black hole's gravitational grip influences not only the swirling accretion disk, but also the broader environment, revealing patterns of energy transfer and matter circulation that were previously inaccessible. Beyond the jets themselves, Chandra's keen X-ray vision has illuminated the subtle behavior of the stellar wind from the companion star in the Cygnus X-1 system. By analyzing the spectral fingerprints in the X-rays, scientists can decipher the composition, temperature, and velocity of this wind, a crucial conveyor of matter feeding the insatiable appetite of the black hole. These insights have transformed our understanding of how binary systems containing black holes evolve, interact, and maintain a delicate cosmic dance over millions of years. Interferometry, a technique that combines signals from multiple telescopes to function as a single, vastly larger instrument, has dramatically amplified our capacity to observe distant phenomena. By measuring the minute differences in the arrival times of light waves across widely separated telescopes, astronomers can reconstruct extraordinarily detailed images of far-off objects, surpassing the resolution limits of any single telescope. In the case of Cygnus X-1, interferometric observations have been revolutionary. This binary system, where a black hole orbits a massive blue supergiant star, has revealed its secrets thanks to radio and optical interferometry. Radio interferometry has tracked the precise trajectories of the energetic jets expelled near the black hole, shedding light on the forces at play and the mechanisms governing jet formation. Optical interferometry has allowed astronomers to pinpoint the system's distance from Earth with unprecedented precision, a vital parameter for calculating the black hole's mass, spin, and gravitational influence. These techniques have also unveiled the detailed structure of the accretion disk, showing how matter behaves under extreme gravitational stress, spiraling inexorably toward the event horizon. Gravitational wave detectors have added an entirely new dimension to our study of compact objects like Cygnus X-1, opening a portal into the hidden dynamics of space-time itself. Instruments such as the Laser Interferometer Gravitational Wave Observatory, or LIGO, can detect the faint ripples in spacetime produced by massive cosmic events. While Cygnus X-1's stable binary orbit does not generate detectable waves at present, these observatories are essential for understanding the physics governing similar systems, particularly during cataclysmic mergers of black holes. When two black holes collide, the resulting gravitational waves carry encode information about their masses, spins, and other properties, offering a direct test of general relativity and a window into the life cycles of these enigmatic objects. By studying these signals, scientists can contextualize systems like Cygnus X-1 within the broader cosmic population of black holes, refining models of their formation, evolution, and eventual fate. Future observational technologies promise to deepen our understanding of Cygnus X-1 even further. Next-generation X-ray telescopes, with far greater sensitivity and resolution, will allow astronomers to examine the accretion disk in extraordinary detail, tracing the motion of hot gas as it plunges toward the event horizon. Advanced gravitational wave observatories, both terrestrial and space-based, may one day detect subtle ripples produced by interactions between the black hole and its companion star, revealing mass exchanges, spin dynamics, and orbital evolution with unmatched precision. Large arrays of radio telescopes, spanning continents or even deployed in space, could generate high-resolution images that resolve the shadow of the black hole against the glowing backdrop of infalling material, providing one of the most stringent tests of Einstein's theory of general relativity in an extreme environment. Even neutrino detectors, while primarily designed for other cosmic phenomena, may capture high-energy particles produced in the dense, searing environment around Cygnus X-1, offering a complementary perspective on its physics. In a more human dimension, the story of Cygnus X-1 is intertwined with some of the greatest minds of theoretical physics. In 1974, Stephen Hawking and Kip Thorne engaged in a memorable wager over the nature of this enigmatic object. Hawking, skeptical of the existence of black holes, contended that Cygnus X-1 was not truly one, while Thorne, confident in the interpretation, argued the opposite. The stakes were unusual yet playful. A 1-year subscription to a satirical magazine for Hawking, or a 4-year subscription to a more risque publication for Thorne. This wager illustrated the scientific uncertainty of the time and the willingness of even the brightest minds to challenge prevailing assumptions. By 1990, as observational evidence mounted, Hawking conceded, marking a milestone in the acceptance of black holes as real astrophysical objects and highlighting the evolving nature of scientific knowledge. The discovery of Cygnus X-1 in 1964 sent ripples of astonishment through the astronomical community. This intense X-ray source, nestled in the constellation Cygnus, defied traditional stellar models. The energy it emitted from an astonishingly compact region far exceeded anything conventional stars could produce. Astronomers gradually recognized that they were observing a phenomenon unlike any previously documented: a black hole. An object so dense that not even light could escape its gravitational clutches. Though black holes had been theoretically predicted decades earlier as solutions to Einstein's general relativity equations, Cygnus X-1 represented one of the first tangible glimpses into these extreme entities, bridging the gap between abstract theory and observable reality, and forever transforming our view of the cosmos. However, many scientists initially treated black holes as purely theoretical constructs, skeptical that such extreme, almost fantastical objects could exist in the tangible universe. The discovery of Cygnus X-1 forced the astronomical community to confront an unsettling possibility. These cosmic monsters were not merely mathematical curiosities confined to equations, but real, physical entities silently orbiting within our galaxy, hidden in the darkness. This revelation ignited a fervent period of debate, observation, and theoretical exploration. Some researchers eagerly embraced the interpretation of Cygnus X-1 as a black hole, seeing it as a groundbreaking confirmation of Einsteinian predictions, while others searched for alternative explanations, reluctant to abandon established models. The controversy surrounding Cygnus X-1 catalyzed significant progress in astrophysics, driving scientists to refine their understanding of extreme celestial phenomena and the fundamental fabric of space and time. When astronomers first detected Cygnus X-1 in the early 1960s, they were confronted by an enigmatic source emitting X-rays of unprecedented intensity. Various hypotheses emerged, reflecting the limits of contemporary astronomical knowledge. One early suggestion was that Cygnus X-1 might be a neutron star, a remnant core left behind after a massive star explodes in a supernova, known for its dense, compact nature and X-ray emissions. Yet the extraordinary luminosity of Cygnus X-1 challenged this interpretation. Another proposal considered the object as a white dwarf accreting matter from a companion star, a scenario known as a cataclysmic variable, capable of producing X-rays, though not at the extreme levels observed in Cygnus X-1. Some astronomers speculated even more wildly, hypothesizing clusters of smaller objects or previously unknown celestial bodies. As observational data accumulated over the years, these alternative explanations gradually fell away. Cygnus X-1 emerged as a black hole residing in a binary system with a massive blue supergiant star. Its path to acceptance was slow and meticulous, unfolding across decades of research. In 1964, when the powerful X-ray source was first cataloged, the concept of black holes was largely confined to theoretical physics, and widespread skepticism permeated the scientific community. Over the course of the 1970s, incremental evidence began to suggest that Cygnus X-1 might indeed harbor a black hole. Astronomers discovered that it was part of a binary system, orbiting a massive blue supergiant, and its X-ray emissions exhibited rapid variability, an indicator of a compact object with immense gravitational pull. Yet alternative interpretations, particularly the possibility of a neutron star, still persisted. Throughout the 1980s and 1990s, advancements in observational techniques fueled more precise measurements. Astronomers calculated the system's mass and realized the compact object was far too massive to be a neutron star, strengthening the black hole hypothesis. Skeptics, however, cautioned that gaps in understanding of stellar evolution and compact objects could leave room for other explanations. It was not until the early 2000s that a broad consensus began to solidify. High-resolution observations combined with sophisticated theoretical modeling provided compelling evidence that Cygnus X-1 was, in fact, a stellar mass black hole. By 2011, detailed studies of the system's mass, orbital dynamics, and emissions convinced the majority of astronomers that Cygnus X-1 was one of the clearest examples of a black hole within our galaxy. The verification of Cygnus X-1 as a black hole relied on decades of painstaking observation. Radio and X-ray telescopes revealed an incredibly compact and massive object orbiting a blue supergiant star, too dense to be a neutron star or any other known stellar remnant. Careful calculations of orbital motions determined that the invisible companion's mass exceeded 6 times that of the Sun, surpassing the theoretical upper limit for neutron stars and leaving a black hole as the only viable explanation. Observations also detected powerful jets of matter being expelled at nearly the speed of light, a hallmark of the extreme gravitational influence of black holes. Moreover, the X-ray spectrum and its variability matched theoretical predictions for matter plunging toward an event horizon consistent with general relativity's description of black holes. Later, with the advent of gravitational wave astronomy, independent confirmation of stellar mass black holes reinforced these conclusions. The discovery of Cygnus X-1 in 1964 marked a watershed moment in astrophysics, transitioning black holes from theoretical speculation to observable reality. As the first strong candidate for a stellar mass black hole, it offered astronomers a tangible laboratory for studying these enigmatic objects. The binary system, comprising a luminous blue supergiant and an invisible dense companion, exhibited intense X-ray emissions that defied conventional explanations. The gravitational dominance of the invisible companion over its massive stellar partner signaled the presence of a compact object far beyond the mass limits of neutron stars, solidifying the black hole interpretation. Cygnus X-1 also revolutionized the study of accretion disks, the swirling bands of matter spiraling into black holes. Observations of this system illuminated how matter behaves under extreme gravitational forces, providing crucial insights into the processes that power some of the universe's most energetic and violent phenomena. The data gleaned from decades of study transformed theoretical predictions into observable science, refining models of X-ray emissions, jet formation, and the complex interactions within binary systems. By bridging theory and observation, Cygnus X-1 not only confirmed the existence of black holes, but also opened a new frontier for understanding the most extreme environments in the cosmos, leaving an indelible mark on the history of astrophysics. Furthermore, Cygnus X-1 catalyzed a profound transformation in the way astronomers approach the cosmos, sparking the development of innovative observational techniques and groundbreaking technologies. The challenge of studying this enigmatic object across multiple wavelengths necessitated unprecedented collaboration between diverse branches of astronomy, from radio and X-ray astronomers to theoretical astrophysicists, establishing a model for the multi-messenger approach that now defines modern astrophysics. This discovery not only confirmed the existence of black holes, but also opened a vast and uncharted frontier in our exploration of the universe. The intense debates surrounding Cygnus X-1 offer a window into the scientific process itself, revealing the meticulous reasoning, skepticism, and evidence-driven inquiry that propel our understanding of extreme cosmic phenomena. Discovered in 1964, Cygnus X-1 immediately ignited intense discussion among astronomers and physicists, forcing them to confront the possibility of objects previously relegated to theoretical curiosities. At the time, black holes were widely viewed as mathematical abstractions rather than tangible cosmic realities. Yet the observations of Cygnus X-1 provided compelling, direct evidence for a massive compact object whose properties could be explained only by the existence of a black hole. The scientific community, initially cautious and often divided, was gradually compelled to acknowledge the reality of these extraordinary entities. The debates surrounding Cygnus X-1 also underscore the critical role of technological advancement in shaping scientific discovery. As instrumentation and observational techniques improved, researchers accumulated increasingly precise data, allowing for a progressively stronger case supporting the black hole interpretation. This illustrates how scientific progress often hinges not only on theoretical insight, but on our ability to observe and measure the universe with ever greater accuracy. Perhaps most strikingly, the Cygnus X-1 saga exemplifies the interplay between healthy skepticism and evidence-based consensus. Even preeminent physicists such as Stephen Hawking, who once bet against the black hole interpretation, ultimately revised their views in response to overwhelming observational proof. The willingness to adapt one's theories in light of new evidence remains a cornerstone of scientific advancement, offering lessons that resonate far beyond the realm of astrophysics. Cygnus X-1 serves as a cosmic laboratory for testing Einstein's theory of general relativity, providing a rare opportunity to probe gravity under extreme conditions. This binary system comprises a blue supergiant star locked in orbit around a black hole, creating an ideal setting to observe relativistic effects firsthand. The black hole's intense gravitational field dramatically warps space-time, allowing scientists to measure phenomena predicted by general relativity. Matter drawn from the companion star spirals toward the black hole, forming an accretion disk that emits powerful X-rays. These emissions yield critical insights into the structure of space-time near the event horizon, a region where gravitational forces are so extreme that they fundamentally alter the behavior of matter and light. One of the most compelling aspects of Cygnus X-1 is its role in testing the no-hair theorem, which posits that black holes can be fully described by just three properties: mass, spin, and electric charge. By analyzing X-ray emissions and the orbital dynamics of the binary system, researchers can rigorously test this principle and search for any deviations that might suggest modifications to our understanding of gravity. Furthermore, Cygnus X-1 offers an invaluable glimpse into the strong field regime of general relativity, where gravitational effects are most extreme. Observations of this system provide vital clues bridging the gap between general relativity and quantum mechanics, inching closer to the elusive goal of a unified theory of quantum gravity. The cosmic laboratory of Cygnus X-1 has yielded striking confirmations of Einstein's predictions. The presence of an event horizon, a defining feature of black holes, is inferred from the abrupt cutoff of X-ray emissions as matter reaches a critical radius beyond which escape is impossible. Time dilation, another consequence of extreme gravity, is observable in the slowed progression of matter near the black hole compared to regions farther away. Even the black hole's apparent simplicity, fully described by mass, spin, and charge, aligns perfectly with the no-hair theorem, despite the complexity of its formation. Time itself is profoundly distorted near Cygnus X-1. As one approaches the event horizon, time slows dramatically relative to distant observers. To a hypothetical observer near the black hole, time would appear to flow normally, while the outside universe seems to accelerate. Approaching the horizon, this effect reaches its extreme, with time nearly halting from an external perspective. Such phenomena are not merely theoretical curiosities, but observable consequences of the black hole's immense gravity, offering tangible evidence of relativistic effects at work. Gravity also bends the path of light, producing the phenomenon of gravitational lensing. In essence, the black hole acts as a cosmic magnifying glass, bending and distorting the appearance of distant objects. While Cygnus X-1 itself is not massive enough to generate dramatic lensing, its observations can be subtly influenced by lensing from other objects along the line of sight. This effect can alter perceived brightness or create slight distortions, further enriching the data astronomers collect from this extraordinary system. Cygnus X-1 represents a nexus of theory, observation, and technological innovation. Its study continues to illuminate the behavior of matter and energy under the universe's most extreme conditions, testing the limits of our scientific understanding, while offering tantalizing glimpses into the profound and often counterintuitive nature of space-time itself. Each photon captured, each fluctuation in X-ray intensity, and each subtle shift in orbital dynamics serves as a testament to the enduring power of curiosity, rigorous observation, and the human drive to unravel the cosmos. Moreover, the immense gravitational pull of Cygnus X, a black hole of staggering density, warps the very fabric of space-time around it, creating a localized gravitational lensing effect. Light from its companion star or from the searingly hot accretion disk spiraling into the black hole bends in ways that allow scientists to probe the black hole's properties with extraordinary precision. Observing this bending of light offers a window into the most extreme environments in the universe, where gravity reigns supreme and provides critical tests of Einstein's theory of general relativity. In systems like Cygnus X-1, gravitational lensing does not merely reveal distant stars or galaxies, it illuminates the invisible, exposing the dynamics of matter caught in the black hole's relentless grasp and offering insight into the distribution of mass across the cosmos. As observational technology evolves, the potential for discovery expands, opening new avenues to understand these enigmatic cosmic objects. Cygnus X-1, one of the first black hole candidates ever identified, has become a linchpin in the study of extreme astrophysics. The system comprises a luminous blue supergiant locked in orbit with an unseen companion, a stellar mass black hole whose presence is inferred from its gravitational influence. By tracking the motion of the supergiant and observing the behavior of material in its vicinity, scientists have gained profound evidence supporting the curvature of space-time, a central tenet of general relativity. One of the most striking phenomena revealed by Cygnus X-1 is frame dragging, where the rotation of the black hole twists space-time itself, dragging it along like a whirlpool in a cosmic ocean. Known as the lens dithering effect, this interaction demonstrates that massive, spinning objects can alter the very structure of the universe. These observations have extended our understanding of gravity from abstract equations into tangible, observable phenomena, bridging theory and reality in ways once thought impossible. The swirling accretion disk of Cygnus X-1 has also served as a natural laboratory, illuminating the behavior of matter at the precipice of the event horizon, the invisible boundary beyond which nothing escapes. By studying the light and X-rays emitted as material spirals inward, researchers can test predictions of general relativity under extreme conditions, refining models of how space-time contorts and responds to immense gravitational forces. The insights gained from these studies have profound implications, not only for understanding black holes, but for comprehending the fundamental structure of the universe. Even decades after its discovery, Cygnus X-1 continues to challenge and inspire scientists. Directly probing the space-time just outside its event horizon remains a tantalizing goal, offering the promise of either confirming Einstein's predictions with unprecedented precision or revealing new physics beyond our current theories. Observing the gravitational waves generated by this system, ripples in space-time itself, could provide yet another dimension of insight, capturing the dynamic interplay between the black hole and its companion in ways that were inconceivable just a few years ago. Future observations hold the potential to measure continuous gravitational waves as the black hole spirals ever closer to its stellar partner, offering unparalleled glimpses into the warping of space-time under extreme gravity. X-ray and radio emissions from the innermost regions of the accretion disk allow astronomers to probe the innermost stable circular orbit predicted by general relativity, testing whether the equations that govern the cosmos hold true even under the most violent conditions imaginable. Cygnus X-1 remains more than a distant object of study. It is a cornerstone of modern astrophysics, a proving ground for theories of gravity, and a vivid reminder of the universe's capacity to challenge and expand our understanding. With each observation, it deepens our comprehension of space-time, gravity, and the extraordinary physics that govern the cosmos, revealing a universe far stranger and more intricate than we ever imagined. Furthermore, long-term monitoring of the orbital dynamics of the Cygnus X system could unveil subtle, almost imperceptible effects predicted by Einstein's theory of general relativity, such as the slow, graceful precession of the orbit caused by frame dragging. Observing these phenomena offers an extraordinary opportunity to test the boundaries of physics in an environment where the principles of both special and general relativity interact in extreme ways. Each precise measurement could either reinforce Einstein's legacy or hint at entirely new physics waiting to be discovered. Relativistic jets are among the most powerful and enigmatic structures in the cosmos. These streams of particles and energy erupt from the poles of certain celestial bodies at velocities approaching the speed of light, extending for thousands, sometimes even millions of light years, making them some of the largest and most spectacular phenomena in the universe. While typically associated with active galactic nuclei that host supermassive black holes at the centers of galaxies, relativistic jets also emerge in smaller systems, such as binary star systems containing stellar mass black holes. Cygnus X-1 stands as a striking example of such a binary system. At its heart is a blue supergiant star locked in orbit around a black hole with a mass roughly 15 times that of our Sun. As material from the star is drawn toward the black hole, it forms a luminous accretion disk, a churning vortex of gas heated to extraordinary temperatures. Yet not all of this material succumbs to the black hole's gravitational grip. Some is accelerated and ejected as twin jets from the black hole's poles. These jets were first detected in the 1970s, marking Cygnus X-1 as one of the earliest known sources of relativistic jets within our galaxy. The jets of Cygnus X-1 are powered by the intense interplay of gravity and magnetism near the black hole. Particles are propelled to near-light speeds, transforming the surrounding space into a dynamic laboratory for astrophysicists. Observations over decades have shown that these jets are not static. They can fluctuate in intensity and orientation, revealing the turbulent and ever-changing environment around the black hole. This makes Cygnus X-1 an invaluable cosmic laboratory for studying black hole physics, relativistic jet formation, and the behavior of matter under conditions that cannot be replicated on Earth. Compared to other cosmic jet-producing systems, Cygnus X-1's jets are remarkable for their relative stability and persistence. Many black holes exhibit intermittent or sporadic jet activity, but the outflow from Cygnus X-1 remains remarkably steady. This consistency allows scientists to study the jets in fine detail, providing critical insights into the mechanisms that govern such extraordinary phenomena. While they are more energetic and far-reaching than jets produced by neutron stars or white dwarfs, Cygnus X-1's jets remain small compared to the colossal jets of supermassive black holes, which can extend for millions of light years, reshaping entire galaxies and influencing galactic evolution on unimaginable scales. The jets themselves are composed of highly energetic particles and electromagnetic radiation. Electrons, protons, and other subatomic particles are accelerated to nearly the speed of light, sometimes accompanied by heavier nuclei or trace neutral atoms. Their composition varies depending on the source. Jets from supermassive black holes are rich in electrons and positrons, energized by intense magnetic and gravitational forces, while jets from protostars or young stellar objects may contain a larger proportion of ionized atoms and molecules, helping to regulate star formation by carrying away excess angular momentum. Regardless of origin, these jets emit a spectrum of electromagnetic radiation, including radio waves, visible light, X-rays, and occasionally gamma rays, allowing astronomers to probe their nature from across the universe. As these jets stream outward, they collide with the interstellar medium, triggering a cascade of complex interactions. High-energy particles moving at near-light speeds slam into stationary clouds of gas and dust, generating intense shock waves that compress and heat the surrounding material to extraordinary temperatures. These interactions create vast bubbles or cavities in the interstellar medium, sweeping away gas and dust along their path. This phenomenon, known as jet-induced feedback, can dramatically influence the distribution of matter within a galaxy, alter star formation rates far from the black hole, and shape the evolution of entire galactic environments, leaving a lasting imprint on the cosmos itself. Cygnus X-1 is more than a celestial object. It is a window into the violent, dynamic processes that govern our universe, a testament to the power of gravity and magnetism, and a living example of the profound mysteries that continue to challenge our understanding of space, time, and energy. Its jets are not merely streams of particles, but the visible echoes of forces that shape galaxies, a narrative of motion and energy that stretches across thousands of light years, reminding us of the immense and intricate complexity of the universe we inhabit. Moreover, the interaction between the jets and the interstellar medium can produce breathtaking and intricate cosmic spectacles. As these relativistic jets surge through space, they carve pathways of astonishing complexity, forming colossal lobes, radiant hotspots, and delicate filaments visible across the electromagnetic spectrum, from radio waves to X-rays. These structures do not merely inhabit the confines of their host galaxies, they extend outward for hundreds of thousands of light years, reshaping the surrounding cosmic landscape in ways that are both subtle and profound. Observing these interactions offers scientists a rare glimpse into the mechanisms of energy transfer within galaxies and highlights the pivotal role that active galactic nuclei play in the evolution and life cycle of their host galaxies. By studying the far-reaching influence of these jets, astronomers uncover the deep and intricate connection between supermassive black holes and the galaxies they dominate. The jets themselves are extraordinary phenomena, composed of high-energy particles traveling at nearly the speed of light and radiating across the cosmos. They serve as a unique window into the extreme physics that govern black holes and their immediate environments. Through detailed observation of these jets, researchers gain insight into the process of accretion, where matter spirals inward toward the black hole, heating to unimaginable temperatures and releasing vast amounts of energy. This process is fundamental to understanding how black holes feed, grow, and influence their surroundings over cosmic timescales. Magnetic fields play an equally critical role in shaping and propelling these jets, guiding their trajectory across immense distances. The structure and composition of the jets reveal the behavior of matter under the influence of extraordinary gravitational forces, offering scientists an unparalleled laboratory for testing the laws of physics in conditions that cannot be replicated on Earth. These cosmic jets also present a rare opportunity to examine Einstein's theory of general relativity in its most extreme natural environment, allowing for exploration of potential new physics beyond our current understanding. Cygnus X-1, a particularly powerful X-ray source within our galaxy, exemplifies the dramatic impact of these jets. Its relativistic outflows stretch across vast expanses of space, interacting with nearby gas and dust, generating shock waves and heating the interstellar medium. As the jets advance, they carve immense cavities and push aside interstellar material, sometimes compressing clouds of gas to the point of igniting new star formation. The radiation emitted by these jets ionizes surrounding gas, creating glowing nebulae that shine brilliantly when observed through telescopes. Beyond shaping their immediate neighborhood, The jets distribute heavy elements formed near the black hole, enriching distant regions of the galaxy and influencing its chemical evolution on a grand scale. Astronomers employ a sophisticated array of observational technologies to study these phenomena. Radio telescopes, such as the Very Large Array in New Mexico, detect the synchrotron radiation produced by electrons spiraling through magnetic fields, mapping jet structures in remarkable detail. Space-based X-ray observatories, including the Chandra X-ray Observatory and XMM Newton, reveal the hottest, most energetic regions of the jets, capturing particles accelerated to near-light speeds. Gamma-ray observatories, both terrestrial and orbital, track the highest energy emissions resulting from jet interactions with surrounding radiation fields. Optical and infrared telescopes further complement these studies by observing the host galaxies and the regions where jets sculpt the interstellar medium. Computational simulations then integrate this extensive data, enabling scientists to reconstruct the full dynamical behavior of these extraordinary cosmic phenomena. Cygnus X-1, with a mass roughly 15 times that of our Sun, exerts a gravitational influence so immense that it warps the very fabric of spacetime. Its presence affects nearby stars, stripping away outer layers and feeding material into its accretion disk, which becomes heated to extreme temperatures and emits intense X-rays detectable from Earth. Surrounding gas clouds are likewise impacted. Compression from the black hole's gravitational pull can spark the formation of new stars, demonstrating the profound role of black holes as both destroyers and creators within their galactic neighborhoods. The study of jets like those from Cygnus X-1 illuminates the astonishing power and complexity of our universe. It bridges the gap between theoretical physics and observable phenomena, revealing the intimate connection between cosmic behemoths and the vast galactic ecosystems they inhabit, and offering a window into the extreme processes that shape the evolution of galaxies across billions of years. Additionally, the black hole unleashes colossal jets of particles that surge outward from its poles at velocities approaching the speed of light. These extraordinary streams of matter pierce through the cosmic void, traveling immense distances and colliding with the surrounding interstellar medium, heating and stirring it as they go. The interplay between Cygnus X-1 and its cosmic environment forms a natural laboratory for astronomers, offering a rare opportunity to study the extreme and often violent physics governing black holes, as well as their profound effects on the matter that drifts nearby. Through careful observation of these turbulent processes, scientists continually refine our understanding of the fundamental forces that shape the universe on both grand and minuscule scales. Cygnus X-1, a formidable black hole residing within our Milky Way galaxy, exerts an astonishing gravitational influence over its surroundings. This cosmic titan, boasting a mass approximately 15 times greater than that of our Sun, warps the fabric of spacetime itself in its immediate vicinity. Its gravitational pull is so immense that it commands everything within several light years, reshaping the motion of stars, gas, and dust alike. The most dramatic illustration of this power is observed in its binary companion, a luminous blue supergiant star locked in an intricate cosmic dance. Gradually, the black hole siphons its material from the star's outer layers, feeding an accretion disk of superheated gas that spirals into its depths. This relentless transfer not only dictates the fate of the companion star, but also redistributes matter throughout the surrounding space, sculpting the interstellar environment in profound ways. Beyond its immediate stellar partner, Cygnus X-1's influence extends to the motions of nearby stars and the dispersal of interstellar matter. Its gravitational grip can subtly redirect stellar orbits and influence the formation of new stars, impacting the galactic neighborhood across several parsecs. In a broader sense, Cygnus X-1 is an active participant in the dynamics of our galaxy, shaping the distribution of gas, dust, and newly forming stars. The intense radiation emitted by its accretion disk, combined with the forceful gravity of the black hole, interacts with the interstellar medium over vast distances, altering the conditions under which stars are born and dictating the flow of cosmic material. Cygnus X-1 shines as a powerful X-ray source, its energy output a beacon in the Milky Way that reveals the hidden mechanisms of the universe. Within this binary system, the black hole continuously draws matter from its supergiant companion, forming a roiling disk of gas heated to millions of degrees. This process generates intense X-ray emissions and propels jets of particles at nearly light speed into the surrounding space. As these jets collide with the interstellar medium, they inject both energy and matter, influencing the composition and behavior of nearby gas clouds, potentially triggering or suppressing star formation depending on the local environment. This creates a complex feedback system where the black hole's activity actively governs the availability of material for future stars, shaping the long-term evolution of the surrounding galactic region. The gravitational might of Cygnus X-1 also orchestrates the motions of nearby stars and molecular clouds, compressing some regions while dispersing others. This combination of gravity and energetic radiation positions the black hole as a central architect in the ongoing cosmic interplay of matter and energy, subtly guiding the evolution of its local section of the Milky Way. As a stellar mass black hole, Cygnus X-1 exemplifies the vital role such objects play in galactic evolution. These dense remnants of massive stars act as cosmic recyclers, drawing in gas and dust only to expel portions of it through high-energy jets, redistributing matter and energy throughout the galaxy. Their radiation can ionize nearby gases, altering the ability of these regions to collapse into new stars, and their gravitational influence can scatter stars across the galaxy, subtly reshaping its structure over eons. Studying Cygnus X-1 allows scientists to glimpse the life cycles of massive stars and the intricate mechanisms that govern galactic ecosystems. Observing its interactions with surrounding matter reveals the complex interconnections between stars, gas, and black holes, offering insight into the grand cosmic narrative of creation, destruction, and transformation. Cygnus X-1's radiation, dominated by high-energy X-rays and gamma rays, ionizes surrounding gas clouds, stripping electrons from atoms and generating vast regions of glowing plasma. These regions can both ignite new star formation by compressing gas clouds and inhibit it by dispersing molecular clouds, demonstrating the black hole's dual role as both creator and destroyer. The jets ejected from Cygnus X-1, moving at nearly the speed of light, produce massive shock waves upon colliding with interstellar material. These shocks heat the gas to extraordinary temperatures, causing it to radiate across a spectrum of wavelengths, from radio waves to X-rays, and profoundly altering the environment around the black hole. Through these violent yet mesmerizing interactions, Cygnus X-1 continues to shape the cosmos around it, serving as a testament to the raw, transformative power of black holes and their ability to influence not just individual stars, but the very structure and evolution of galaxies themselves. Furthermore, the immense radiation and particle jets emanating from Cygnus X-1 play a pivotal role in shaping the energy balance of the interstellar medium surrounding it. This continuous influx of energy profoundly influences the motion and dynamics of nearby star systems, altering their trajectories and interactions. It also fundamentally changes the chemical makeup of the surrounding space, breaking apart existing molecules while creating a host of new ionic species, transforming the environment on a molecular level. The extensive impact of Cygnus X-1 highlights the remarkable influence that compact, high-energy objects can exert on their cosmic neighborhoods. For astronomers, Cygnus X-1 acts as an extraordinary natural laboratory, offering an unparalleled window into the mechanisms of cosmic feedback and the interplay between matter and energy in extreme conditions. As one of the brightest X-ray sources in our galaxy, Cygnus X-1 is a binary system composed of a blue supergiant star locked in a gravitational dance with a stellar mass black hole. The black hole's intense gravitational pull relentlessly draws matter from its stellar companion, forming a swirling accretion disk of gas heated to extraordinary temperatures. This ongoing process of mass transfer and accretion generates highly energetic jets of particles that stream out from the black hole's poles at velocities approaching the speed of light. As these jets pierce through the interstellar medium, they trigger shock waves that propagate over vast distances, altering the physical and chemical state of the surrounding space. Observing these interactions allows scientists to understand how black holes regulate their own growth while simultaneously influencing the evolution of their host galaxies. The feedback mechanisms at work in Cygnus X-1 exemplify the delicate balance between matter and energy in the most extreme cosmic environments. As the black hole consumes matter from its companion, it simultaneously ejects a portion of it back into space, effectively self-regulating its feeding process. This dynamic equilibrium between inflow and outflow has profound consequences for the surrounding galactic system, shaping the distribution of gas, dust, and newly forming stars over enormous scales. By studying Cygnus X-1, researchers gain insight into the ways similar feedback processes may operate in distant galaxies, providing a crucial reference for models of galactic formation and evolution, and illuminating the intricate relationship between supermassive black holes and their host galaxies throughout the universe. Cygnus X-1, with a mass roughly 15 times that of our Sun, exerts a formidable gravitational influence on its surrounding environment. Its immense gravitational field can disrupt nearby gas clouds, preventing them from collapsing into new stars. Yet this same disruption generates turbulence and shock waves in the surrounding medium, compressing other regions of gas and dust in the process. These compressed pockets can become fertile grounds for star formation, triggering the birth of new stars farther from the black hole. The energetic jets of radiation and particles emitted by Cygnus X-1 extend far into space, heating the surrounding gas and forming bubbles of hot plasma. At the edges of these bubbles, conditions can become dense and cool enough to foster further star formation, demonstrating the dual role black holes play in both suppressing and stimulating the formation of stars. Cygnus X-1 is also central to understanding the life cycles of massive stars and the genesis of black holes. As one of the earliest black holes discovered, it has provided astronomers with vital clues about the final stages of stellar evolution. Its story begins with a progenitor star likely more than 40 times the mass of our Sun. When such a colossal star exhausts its nuclear fuel, it typically undergoes catastrophic collapse, often resulting in a spectacular supernova explosion. However, Cygnus X-1 challenges this traditional narrative, suggesting that some extremely massive stars may bypass the supernova stage entirely. Instead, the progenitor star appears to have collapsed directly into a black hole, a process known as direct collapse, where the core's immense mass prevents even the outward force of a supernova from overcoming gravity. The existence of Cygnus X-1 has helped refine astronomers' understanding of stellar mass limits, revealing the critical thresholds that determine whether a massive star becomes a black hole or a neutron star. This knowledge provides essential insight into the ultimate fate of massive stars across the cosmos, offering clues about the processes that shape galaxy evolution. Located approximately 6,000 light-years from Earth, Cygnus X-1 continues to be one of the most closely studied systems in our galaxy. Its composition, a blue supergiant orbiting an invisible stellar mass black hole, offers a unique laboratory for examining the extreme physics of black hole environments. As matter from the blue supergiant spirals toward the black hole, it forms an accretion disk, where friction and compression heat the gas to extraordinary temperatures, producing powerful X-ray emissions detectable from Earth. These emissions allow scientists to probe the complex interactions of matter under extreme gravity, temperature, and energy conditions. Through Cygnus X-1, astronomers can witness firsthand the forces that govern the lives and deaths of the most massive stars, the formation of black holes, and the profound influence these objects have on their cosmic surroundings. The system study not only illuminates the behavior of matter in extreme conditions, but also enriches our understanding of the cosmic cycles of star formation, energy distribution, and galactic evolution on scales spanning thousands of light years. Furthermore, Cygnus X-1 exemplifies the extraordinary precision of Einstein's theory of general relativity, offering a living testament to the predictive power of his groundbreaking equations. The system's remarkable properties, from the precise orbital period of its two constituents to the immense gravitational forces at play, align almost perfectly with theoretical forecasts, confirming long-held predictions about the behavior of matter under extreme gravitational conditions. As a result, Cygnus X-1 not only illuminates the final chapters in the life cycles of stars, but also functions as a cosmic laboratory where the most sophisticated physical theories can be put to the test under natural, extreme conditions. Cygnus X-1 represents a profound enigma, a celestial anomaly that has compelled astronomers to reassess long-standing models of stellar evolution and collapse. At the heart of this extraordinary system is a luminous blue supergiant star locked in orbit around an invisible companion of staggering density. The invisible companion exerts an enormous gravitational influence on its surroundings, producing effects that leave little doubt. It is a black hole. Yet what sets Cygnus X-1 apart is not merely the presence of a black hole, but its exceptional mass. Unlike typical black holes formed from the death of massive stars, this black hole is estimated to weigh approximately 15 times the mass of our Sun, far exceeding the expectations of conventional stellar collapse models. The discovery of such a massive black hole has challenged traditional theories of stellar death. It suggests the possibility that some stars may collapse directly into black holes without undergoing a supernova explosion, a phenomenon known as a failed supernova. This revelation forces scientists to rethink the final evolutionary stages of the universe's most massive stars. In particular, it raises questions about the processes by which massive stars lose mass, the role of their rotational speeds, and how variations in their chemical composition might influence the formation of unusually massive black holes. Cygnus X-1 provides a crucial window into these processes, helping astronomers understand the complex interplay between a star's initial mass, its life cycle, and the ultimate mass of the black hole it leaves behind. The binary nature of Cygnus X-1, with a blue supergiant companion orbiting a massive black hole, offers researchers a rare and invaluable opportunity to observe the physics of black holes and the dynamics of stellar evolution in real time. By studying the system, scientists have established that stars with initial masses exceeding roughly 20 to 25 times that of the Sun are prime candidates to end their lives as black holes. Furthermore, observations indicate that the progenitor star of Cygnus X-1 must have shed a significant fraction of its mass prior to collapse, refining our understanding of how stellar mass loss affects the formation of black holes and the distribution of matter in galaxies. Cygnus X-1 also sheds light on the influence of metallicity, the abundance of elements heavier than hydrogen and helium, on black hole formation. While earlier theories suggested that only stars with low metallicity could give rise to black holes, the composition of this system demonstrates that even stars with relatively high metal content are capable of producing these dense, exotic remnants. This insight challenges prior assumptions and enriches our broader understanding of stellar evolution across different cosmic environments. As one of the closest known black holes to Earth, Cygnus X-1 serves as an unparalleled laboratory for the observation and study of these enigmatic objects, offering a rare opportunity to witness the processes that govern the life and death of massive stars. The system's black hole, having formed from a massive progenitor star, provides a glimpse into the ultimate fate of stars many times more massive than the Sun. By analyzing Cygnus X-1, astronomers can refine models of stellar evolution, allowing more precise predictions of the destinies of other massive stars scattered across the cosmos. The mass and properties of the black hole, along with its blue supergiant companion, offer critical clues about the conditions necessary for a massive star to collapse directly into a black hole, rather than erupt as a supernova. Observations of matter behavior under the black hole's extreme gravitational pull deepen our understanding of physics in environments impossible to replicate on Earth, offering insights into the broader dynamics of galaxies and the life cycle of stars within them. Cygnus X-1's story extends beyond gravitational physics by encompassing the chemical enrichment of the universe. The progenitor star, likely over 40 times the mass of the Sun, underwent nuclear fusion in its core, transforming lighter elements into heavier ones such as carbon, oxygen, and iron. As the star reached the end of its life, a supernova expelled these newly formed elements into space, seeding the cosmos with the essential building blocks for future generations of stars, planets, and ultimately life itself. The study of the materials surrounding Cygnus X-1 enables scientists to quantify the elemental yields of massive stars, advancing our understanding of how the universe became enriched with elements heavier than hydrogen and helium, shaping the diverse and complex cosmos we observe today. The blue supergiant companion of Cygnus X-1, known as HDE 26868, performs a gravitational ballet around its black hole partner, offering a living laboratory for the study of binary star evolution. Continuous mass transfer from the companion to the black hole, driven by stellar winds and gravitational forces, alters the evolutionary trajectories of both objects, potentially accelerating the companion star's own demise. By observing the companion's properties, its temperature, size, and composition, astronomers refine models of massive star aging and interactions within binary systems. This knowledge illuminates the formation of other exotic celestial objects, such as neutron stars, and deepens understanding of the mechanisms behind supernova explosions, enriching the narrative of stellar life and death across the universe. Cygnus X-1 stands as one of the most studied and captivating examples of the interplay between massive stars and black holes. It embodies the extremes of astrophysical phenomena, illustrating how gravity, mass, and stellar composition interact to produce some of the universe's most mysterious and powerful entities. From its role in testing the limits of general relativity to its contribution to understanding chemical evolution and stellar dynamics, Cygnus X-1 remains an indispensable touchstone for astronomers, physicists, and cosmologists alike, providing insight into the forces that have shaped the cosmos on both grand and intimate scales. Furthermore, the existence of this extraordinary binary system fundamentally challenges our understanding of stellar evolution, the lifespans of massive stars, and the complex processes that lead to black hole formation. The characteristics of the companion star, its orbit, and interactions with the black hole provide critical data for reconstructing the history and age of the Cygnus X-1 system. Through careful analysis, astronomers can glean invaluable insights into the precise conditions under which black holes form and evolve within binary systems scattered across the cosmos. Cygnus X-1 presents some of the most extreme and violent conditions ever observed in the universe. At its core, this cosmic powerhouse is a binary system composed of a blue supergiant star locked in a gravitational dance with a black hole. This black hole, possessing a mass roughly 15 times that of our Sun, generates a gravitational field so intense that it warps the very fabric of space-time around it. Approaching its event horizon, gravity becomes so overwhelming that not even light can escape, creating a region where conventional laws of physics begin to falter. Time itself is distorted under these conditions, moving slower near the black hole compared to more distant regions, a phenomenon known as time dilation. The black hole's immense gravity siphons material from its massive companion star, forming an accretion disk of superheated gas and dust. This disk reaches temperatures of millions of degrees, far exceeding the surface of the Sun, and as the matter spirals inward at velocities approaching the speed of light, it releases staggering amounts of energy in the form of X-rays and high-energy radiation. This maelstrom of plasma and radiation transforms Cygnus X-1 into a natural laboratory, allowing scientists to probe the behavior of matter and energy under conditions that could never be replicated on Earth. Observations of this system offer direct tests of Einstein's theory of general relativity, while providing deeper understanding of black hole physics and their profound influence on surrounding space. Located approximately 6,000 light-years from Earth, Cygnus X-1 stands as a beacon of high-energy astrophysics. Its blue supergiant companion star and the black hole create a dynamic interplay where matter is pulled from the star, compressed, and heated to extraordinary temperatures within the accretion disk. The resulting X-ray emissions reach Earth as luminous signatures of processes occurring under extreme gravity, enabling astronomers to decode the intricate physics at work. Patterns in these X-ray emissions reveal details about the structure of the accretion disk, the mass and spin of the black hole, and complex phenomena such as frame dragging, where the rotation of the black hole twists and drags space-time itself. Observing matter at the event horizon, the point of no return, offers a rare glimpse into the ultimate limits of gravity's power. Cygnus X-1 not only illuminates the interactions between black holes and companion stars, but also extends the boundaries of scientific knowledge. By analyzing X-ray variability and plasma behavior within the accretion disk, researchers refine models of matter in extreme gravitational and magnetic fields. The insights gained inform both astrophysics and terrestrial science, influencing studies in plasma physics and fusion energy. In this cosmic crucible, general relativity and quantum mechanics converge, offering unparalleled opportunities to test the laws of physics in environments where traditional assumptions break down. The system's superheated plasma, spiraling inwards under immense gravitational and magnetic forces, emits powerful X-rays that astronomers can detect and analyze from Earth. These emissions reveal the intricate mechanics of high-energy interactions, providing a window into processes that govern the universe on the most extreme scales. Each observation of Cygnus X-1 challenges prevailing theories, driving innovation in our understanding of space, time, gravity, and the extraordinary behaviors of matter under conditions that defy imagination. In every sense, Cygnus X-1 is a cosmic laboratory, a natural experiment in which the universe itself demonstrates the limits of energy, physics, and the enduring mysteries of black holes and the stars they consume. Furthermore, Cygnus X-1 unleashes colossal jets of plasma that are hurled from the vicinity of its black hole at velocities approaching the speed of light. These streams of matter, luminous and fierce, serve as a window into the mysterious processes by which energy can be drawn from a rotating black hole and channeled into accelerating plasma to relativistic speeds. By tracking and analyzing these extraordinary phenomena, astrophysicists refine models of plasma behavior under extreme conditions, offering insights that extend far beyond Cygnus X-1 itself, illuminating the workings of active galactic nuclei, gamma-ray bursts, and other high-energy cosmic events. As a stellar mass black hole within our own galaxy, Cygnus X-1 functions as a natural particle accelerator on a scale that dwarfs any human-built collider. This celestial powerhouse creates environments where particles are propelled to energies so extreme that they rival and often exceed the capacities of the most advanced particle accelerators on Earth. The process begins with the immense gravitational pull of the black hole. Matter from a nearby companion star spirals inward, forming a dense accretion disk that heats to millions of degrees. This superheated plasma becomes a crucible for high-energy particles, while the black hole's rotation, entwined with its formidable magnetic fields, generates a cosmic engine that accelerates these particles to extraordinary speeds. Caught in this cosmic maelstrom, particles are whipped around with dizzying velocity, gaining energy with each revolution. Some are ultimately ejected in powerful jets that streak across light years of space, acting as nature's particle beams and hurling matter at nearly the speed of light. The energies reached in this natural accelerator far surpass anything achievable on Earth. Particles propelled by Cygnus X-1 can attain energies millions of times greater than those produced by the Large Hadron Collider, offering an unparalleled laboratory for studying particle physics under conditions impossible to replicate on our planet. Cygnus X-1, therefore, becomes a rare and invaluable cosmic laboratory, merging astrophysics and particle physics in a single celestial system. This binary star system, composed of a blue supergiant star orbiting a stellar mass black hole, provides scientists a unique vantage point to observe matter under the influence of extraordinarily strong gravitational fields. As the black hole continuously siphons material from its companion, an accretion disk of superheated gas forms, spiraling inward at incredible speeds and temperatures. This movement emits intense X-rays detectable from Earth, allowing researchers to test theories of matter behavior at the edge of the event horizon, where classical physics stretches to its limits. Cygnus X-1's relativistic jets, powerful streams of particles launched from its poles, reveal the mechanisms by which matter can be accelerated to near-light speed. Observing these jets helps scientists understand not only particle acceleration, but also the profound influence such outflows have on the surrounding space. Additionally, the system's variable X-ray emissions offer insights into the structure and dynamics of accretion disks, refining models of black hole growth and their interactions with their environments. These findings illuminate the behavior of both stellar mass black holes and supermassive black holes residing at galactic centers. In this extraordinary laboratory, the laws of physics are tested in ways impossible on Earth. The gravitational pull of the black hole produces extreme conditions where matter falls inward, heats to millions of degrees, and experiences forces that warp time and space itself. Researchers can observe particle behavior under these intense gravitational and energetic conditions, testing predictions from general relativity and quantum mechanics simultaneously. The jets ejected by Cygnus X-1 provide further clues about particle acceleration mechanisms, offering potential parallels to processes studied in terrestrial particle accelerators, bridging cosmic phenomena with human physics research. Yet despite its value, Cygnus X-1 presents formidable challenges as a natural laboratory. Located approximately 6,000 light-years away, the system's distance hampers high-resolution observation, making it difficult to capture subtle phenomena near the event horizon. Its dynamic environment, fueled by the constant feeding of material from its companion star, adds further complexity. The accretion disk and jets are in perpetual flux, creating a shifting laboratory where conditions are never stable for long. Isolating specific effects or conducting controlled experiments becomes a delicate endeavor, as the system's extreme physics operate in a realm of constant motion, intensity, and transformation. In its entirety, Cygnus X-1 exemplifies the awe-inspiring power of the cosmos, a natural laboratory that accelerates particles to unimaginable energies, warps spacetime with its gravity, and emits radiant jets that traverse light years. Every observation brings us closer to understanding the fundamental laws of the universe, revealing the extraordinary interplay between gravity, magnetism, and matter in the most extreme conditions imaginable. The system stands as a testament to the sheer scale of cosmic forces, offering a front-row seat to the violent and beautiful mechanics of a black hole at work. Furthermore, the intense radiation pouring from the accretion disks encircling the black hole creates formidable challenges for astronomers attempting to observe and measure the surrounding phenomena. This extraordinary emission, a torrent of high-energy photons and particles, can easily drown out more delicate signals, making it exceptionally difficult to detect subtle behaviors or gather precise measurements of the black hole's fundamental properties. Despite the remarkable sophistication of current observational technology, it still faces profound limitations when probing the most extreme regions near a black hole. The overwhelming gravitational forces and the extraordinary energy processes in these zones stretch instruments to their limits, leaving some of the most tantalizing mysteries of black hole physics frustratingly just beyond the reach of contemporary science. Cygnus X-1, the first black hole ever discovered, remains a source of fascination and ongoing investigation for astronomers and astrophysicists alike, with a multitude of questions still unresolved. One of the foremost enigmas concerns the exact mass of the black hole. Although researchers have been able to produce reasonable estimates, pinning down a precise figure is extraordinarily difficult due to the complex gravitational interactions between Cygnus X-1 and its companion star. Beyond its mass, the dynamics of the accretion disk itself present a puzzle. Scientists are still unraveling the processes that drive the immense jets of matter that erupt from the vicinity of the black hole. These jets, moving at velocities approaching the speed of light, pose fundamental questions about the extreme physical conditions in such high-energy environments and the forces that channel matter into such focused streams. The evolutionary path of the Cygnus X-1 system adds another layer of mystery. Researchers are working to reconstruct how this binary system originally formed and how it might evolve over cosmic timescales. Understanding both its past and future could illuminate the life cycles of massive stars, the mechanisms behind black hole formation, and the complex gravitational ballet that governs binary systems. Moreover, the influence of Cygnus X-1 on its surrounding cosmic neighborhood continues to be a focal point of study. The immense gravitational pull and radiation emitted by the black hole interact with surrounding gas and dust, potentially regulating star formation and altering the broader structure of its galactic environment. These questions drive an ongoing cycle of observation, simulation, and theoretical research, cementing Cygnus X-1 as a centerpiece in the study of astrophysical extremes. Looking ahead, future space missions promise to transform our understanding of Cygnus X-1 and black holes in general. Next-generation telescopes and instruments could enable observation of Cygnus X-1 with unparalleled clarity, providing unprecedented detail about its interactions with the companion star and the complex structure of the accretion disk. High-resolution, multi-wavelength studies of the disk may reveal the precise mechanics of matter swirling into the black hole, illuminating the processes responsible for launching relativistic jets. Future missions might also aim to measure the black hole's spin with extraordinary precision, a critical parameter for modeling its evolution and assessing its impact on surrounding spacetime. Long-term monitoring of Cygnus X-1 could uncover previously unseen variations in behavior, revealing dynamic processes that challenge current theoretical models. These discoveries would have profound implications for our understanding of the laws of physics under extreme conditions, and for the broader study of cosmic evolution. Achieving this level of insight will require significant technological advances. Improved X-ray telescopes with enhanced sensitivity and resolution will allow astronomers to probe the structure and fluctuations of the accretion disk in unprecedented detail. Sophisticated gravitational wave detectors, both space and ground-based, could capture the subtle ripples in spacetime produced by interactions within the system, offering fresh clues about the black hole's properties and its gravitational influence on the companion star. Advanced radio telescopes and interferometry networks promise to provide sharper, more detailed images of the relativistic jets streaming from Cygnus X-1, elucidating the mechanisms behind their formation and propagation. Meanwhile, the computational power of modern supercomputers and the sophistication of simulation software enable researchers to model the extreme physical conditions surrounding the black hole with increasing accuracy, bridging the gap between observation and theory. Machine learning and artificial intelligence are revolutionizing this field, capable of analyzing massive data sets to detect faint signals and subtle patterns that human researchers might miss. For Cygnus X-1, AI algorithms could track the intricate, rapidly fluctuating X-ray emissions from the accretion disk, highlighting subtle changes that may point to new physical phenomena or confirm theoretical predictions. Similarly, AI could refine our understanding of the companion star by processing complex spectroscopic data, revealing its composition, structural changes, and how it is shaped by the immense gravitational influence of its black hole neighbor. These insights promise to deepen our understanding of stellar evolution in extreme environments, offering a window into the life and death of massive stars and the extraordinary forces that govern black holes and their cosmic domains. Furthermore, machine learning holds the potential to revolutionize our understanding of the intricate gravitational ballet occurring within the Cygnus X-1 system. By simulating millions of possible scenarios and meticulously comparing them with observational data, artificial intelligence could refine our models of black hole physics in ways previously unimaginable. Such computational power might even reveal hidden aspects of general relativity in action, exposing subtle effects that remain undetectable through traditional observational methods. Cygnus X-1, the first black hole ever identified, remains a source of relentless fascination and a catalyst for potential breakthroughs in astrophysics, inviting scientists to probe the very nature of spacetime itself. Future investigations of this cosmic titan are poised to uncover critical insights into the behavior of matter at the precipice of the event horizon, the ultimate boundary where not even light can escape. Advanced instrumentation could allow astronomers to witness these extreme processes in unprecedented detail, offering a chance to confirm, challenge, or expand our current understanding of gravity and the fabric of the universe. Beyond the event horizon, the colossal jets of particles that Cygnus X-1 emits are equally compelling. Accelerated to velocities approaching the speed of light, these jets may hold the secrets of cosmic ray acceleration, shedding light on the most energetic phenomena in the cosmos and their profound influence on galactic evolution. The spin of Cygnus X-1 is another avenue of intense study. Precise measurements of its rotation could illuminate the black hole's formative history and growth patterns. Determining the exact rate of its spin might allow researchers to reconstruct the life cycles of the massive stars from which it originated, offering a clearer picture of the processes that lead to black hole formation. The interactions between Cygnus X-1 and its companion star provide yet another layer of insight, enhancing our understanding of binary star systems and their evolutionary trajectories. These findings have far-reaching consequences for modeling stellar populations and the structure of galaxies, ultimately refining our perspective on the cosmic landscape. Cygnus X-1 stands as a luminous beacon in humanity's quest to understand black holes. Its relative proximity to Earth grants astronomers an unparalleled laboratory to examine these enigmatic objects up close. Data from Cygnus X-1 have already transformed our models of black hole behavior and their dynamic interactions with companion stars. Detailed scrutiny of mass transfer processes between Cygnus X-1 and its stellar companion has yielded insights that guide the search for other hidden black holes within binary systems across the Milky Way. The unique X-ray emissions and gravitational signatures observed in Cygnus X-1 serve as templates, guiding astronomers in locating and studying similar systems elsewhere in the galaxy. The study of Cygnus X-1 has also advanced our understanding of accretion disks, the swirling rings of matter that encircle black holes. These disks are fundamental to the growth and evolution of black holes, and lessons learned from Cygnus X-1 are applicable to the study of other systems, including those vastly different in size or cosmic environment. The cutting-edge techniques and technologies developed to observe Cygnus X-1, from enhanced X-ray detection methods to sophisticated data analysis algorithms, are proving indispensable in the broader hunt for black holes, expanding our capacity to discover rare and exotic objects scattered across the universe. As a stellar mass black hole within our galaxy, Cygnus X-1 functions as a cosmic laboratory for testing the most fundamental theories of gravity and spacetime. First discovered in 1964, it continues to push the boundaries of our understanding of extreme gravitational environments. Its proximity allows for observations of unparalleled precision, enabling astronomers to examine the behavior of matter and energy under immense gravitational forces, potentially refining or challenging the predictions of Einstein's general relativity. Future campaigns targeting Cygnus X-1 are likely to focus on high-precision measurements of its mass, spin, and the structure of its accretion disk. Advanced telescopes combined with cutting-edge data analysis techniques may detect subtle deviations from the expectations of general relativity, hinting at new theories of gravity or suggesting modifications to our current understanding of spacetime. Each observation of Cygnus X-1 not only deepens our comprehension of this singular black hole, but also opens windows into the broader workings of the universe, allowing us to explore phenomena where the extremes of physics are on full display. Additionally, Cygnus X-1 could serve as a groundbreaking instrument in testing and validating some of the most ambitious theories in modern physics, particularly those striving to bridge the seemingly incompatible realms of general relativity and quantum mechanics. Theoretical frameworks such as string theory or loop quantum gravity, which attempt to describe the fabric of space-time at its most fundamental level, could finally find a real-world testing ground through observations of this extraordinary stellar black hole. By offering a tangible laboratory for these abstract ideas, Cygnus X-1 has the potential to illuminate the elusive phenomenon of quantum gravity, guiding scientists closer to a unified understanding of the universe's underlying principles. Since its initial discovery in 1964, Cygnus X-1 has not only captivated the scientific community, but also inspired the imagination of countless creators in science fiction. This formidable source of X-rays, now firmly identified as a black hole, has permeated literature, television, and music, becoming a symbol of cosmic mystery and human curiosity. In novels and short stories, authors often position Cygnus X-1 as a dramatic backdrop where the extremes of space, time, and physics converge. It is frequently portrayed as a portal to other dimensions, a reservoir of unimaginable energy for advanced civilizations, or the ultimate frontier for daring explorers. These narratives take readers on audacious journeys into the heart of the unknown, pushing the boundaries of human understanding and scientific exploration while dramatizing the perilous allure of black holes. On screen, Cygnus X-1 provides an equally compelling visual spectacle. Science fiction television series and films exploit its presence as a narrative device, portraying it as a hazardous anomaly capable of threatening passing starships or as a cryptic celestial entity harboring secrets of the cosmos. Visual depictions often emphasize the black hole's swirling accretion disk, immense gravitational distortions, and the dramatic effects of time dilation, allowing viewers to witness these extraordinary phenomena in vivid, almost tangible detail. The cinematic portrayal transforms abstract scientific concepts into gripping visual experiences, marrying entertainment with education and fostering public fascination with astrophysics. In music, Cygnus X-1 achieved perhaps its most iconic cultural representation through the rock band Rush, which composed a two-part epic song that narrates the journey of an intrepid explorer venturing into the black hole. This artistic endeavor melds rigorous scientific ideas with poetic storytelling, introducing audiences to the real-world astronomical entity while igniting curiosity about the mysteries of black hole physics. The fusion of science and art in this context demonstrates the black hole's profound impact beyond academic circles, influencing popular culture and encouraging broader public engagement with space science. Scientifically, Cygnus X-1 has played an instrumental role in shaping our understanding of black holes. Initially detected during a rocket flight in 1964, its intense X-ray emissions puzzled astronomers and hinted at phenomena beyond conventional stellar processes. Through detailed observation and analysis, scientists recognized that Cygnus X-1 represented the first strong candidate for a black hole within our own galaxy. This identification transformed the concept of black holes from theoretical abstractions into objects, capturing public imagination and stimulating discourse about the fundamental nature of space, time, and gravity. The continued study of Cygnus X-1, particularly in the context of its binary system interactions, has provided invaluable insights into accretion processes, relativistic effects, and the complex dynamics that govern these enigmatic cosmic structures. Its ongoing observation continues to refine and expand our knowledge, bridging the gap between theoretical predictions and empirical evidence, while inspiring generations of scientists, storytellers, and enthusiasts to explore the infinite mysteries of the universe. Moreover, Cygnus X-1 has emerged as an extraordinary gateway for the public to grasp the enigmatic behaviors of black holes, offering a front-row seat to cosmic phenomena that were once purely theoretical. Its dramatic interactions with its companion star reveal a celestial dance both violent and mesmerizing. The luminous accretion disk, spiraling matter into the black hole's depths, and the spectacular jets of plasma shooting outward at unimaginable speeds provide vivid, almost cinematic illustrations of black hole physics. These features have become central in educational materials, documentaries, and popular science books, transforming what was once invisible and abstract into something tangible, almost palpable to the human imagination. The influence of Cygnus X-1 extends far beyond the confines of astrophysics. It has ignited profound conversations about the universe's structure, the boundaries of human knowledge, and our place within the cosmos. By supplying concrete evidence of these extreme celestial objects, Cygnus X-1 has demystified black holes, shifting them from the realm of science fiction fantasies to subjects of rigorous scientific inquiry and widespread public fascination. Artists across disciplines have drawn inspiration from Cygnus X-1, interpreting its mystery and power through a multitude of creative expressions. Painters have produced arresting visuals, often depicting the black hole as a dark, swirling vortex surrounded by luminous gases and distant stars, emphasizing the violent gravitational pull that draws matter inward in streaks of vibrant color. Sculptors have attempted to capture its essence in 3 dimensions, using polished metals, dark stones, or intricate models of the accretion disk and companion star, translating invisible cosmic forces into tangible forms. Digital artists, leveraging advanced graphics and scientific data, have created precise visualizations of Cygnus X-1's environment, from its twisting jets of plasma to the warping of space-time itself, bridging the gap between scientific understanding and public comprehension. Musicians, too, have been inspired by Cygnus X-1, composing works that echo its cosmic drama. Deep resonant tones mimic the black hole's immense gravity, while swirling melodies evoke the turbulence of the surrounding space. Some compositions even incorporate actual radio emissions from the Cygnus region, forging a direct sonic link to this celestial wonder. Cygnus X-1, historically the first strong black hole candidate identified, has also been the source of several persistent misconceptions. Many imagine it as a solitary object, whereas it is in fact a binary system comprising a massive blue supergiant star and the black hole, locked in an intricate orbital dance. Despite its intense X-ray and high-energy emissions, it poses no threat to Earth or nearby star systems. Another common misunderstanding is that Cygnus X-1 is visible to the naked eye. While its host constellation, Cygnus, can be seen from Earth, the black hole itself remains invisible without specialized instruments. We only observe its influence on nearby matter. Some believe Cygnus X-1 is unique, yet astronomers have since discovered numerous black hole binary systems throughout the galaxy and beyond, each contributing to the tapestry of cosmic understanding. The cultural impact of Cygnus X-1 is equally profound. Musicians and composers have immortalized its enigmatic presence in sound, spanning genres from progressive rock to electronic, ambient, and heavy metal. The Canadian band Rush famously dedicated two epic works, Cygnus X-1 Book 1, The Voyage, and Cygnus X-1 Book 2, Hemispheres, exploring space, human curiosity, and the unknown. Electronic and ambient artists craft soundscapes that mirror the infinite expanse and mystery of the cosmos, while heavy metal bands draw on its raw power as a metaphor for unstoppable force or cosmic destruction. Cygnus X-1 serves as a remarkable bridge between science and art, demonstrating how discovery can inspire creativity and imagination across human culture. In education and outreach, Cygnus X-1 remains a cornerstone for engaging learners and the public alike. As one of the most extensively studied celestial objects, it offers a tangible example of complex astrophysical concepts. Its discovery in 1964, during a pioneering rocket flight that identified it as the first widely accepted cosmic X-ray source and strong black hole candidate, marks a historical turning point in our understanding of the universe. Educators use Cygnus X-1 to illustrate accretion disks, X-ray emissions, and the behavior of matter under extreme gravitational forces, turning abstract theory into accessible reality. Its binary system, featuring a black hole and a blue supergiant star, exemplifies the interaction between massive cosmic entities and their surroundings, providing learners with a concrete window into the dynamics of the universe's most mysterious objects. Cygnus X-1 continues to captivate both scientists and the public, serving as a beacon of curiosity, creativity, and discovery. Its story is one of observation, imagination, and inspiration, linking the infinite expanse of space with the human drive to understand, represent, and celebrate the extraordinary forces that shape our cosmos. Furthermore, Cygnus X-1 remains at the cutting edge of astrophysical research, serving as both a beacon and a laboratory for educators to demonstrate how ongoing scientific exploration shapes our understanding of the cosmos. Through detailed observation and sophisticated instruments, including X-ray telescopes and gravitational wave detectors, researchers reveal the intricate methods used to study this enigmatic system. By exposing students and the public to these techniques, Cygnus X-1 inspires the next generation of scientists, while highlighting the evolving, dynamic nature of discovery itself. The tale of Cygnus X-1 has etched itself into the annals of astrophysics as one of the most captivating stories, a cosmic drama that has enthralled both scientists and enthusiasts around the world. The story begins in the 1960s when astronomers first detected an unusually intense source of X-rays emanating from the constellation Cygnus. Unlike other known X-ray emitters, this source resisted conventional explanations, prompting a flurry of investigations. As researchers dug deeper, the realization emerged that they might be witnessing something unprecedented, the first plausible detection of a black hole. This revelation ignited rigorous debate and intense scientific inquiry, eventually leading to one of the most famous intellectual wagers in physics. Stephen Hawking, skeptical of the black hole interpretation, wagered against it, while Kip Thorne, convinced of its existence, accepted the bet. This high-stakes interplay between human curiosity and cosmic mystery added an extraordinary narrative layer to the unfolding astronomical drama. Cygnus X-1 has since been immortalized in numerous documentaries, popular science publications, and even inspired artistic interpretations, demonstrating the profound cultural and scientific impact of its discovery. It exemplifies the process of scientific investigation: observation, hypothesis, experimentation, and debate, all of which drive our understanding of the universe forward. Recent studies continue to refine knowledge of its mass and spin, revealing that Cygnus X-1 is far from a static object. Its evolving profile exemplifies how our comprehension of the cosmos is constantly growing, cementing Cygnus X-1 as an enduring icon in astrophysics. Cygnus X-1 and Sagittarius A star, both black holes, differ markedly in size, formation, and cosmic role. Cygnus X-1 is a stellar mass black hole, the remnant of a collapsed massive star located roughly 6,000 light-years from Earth in the constellation Cygnus. Weighing about 15 times the mass of our Sun, it ranks among the heaviest known stellar black holes. In stark contrast, Sagittarius A star is a supermassive black hole at the center of the Milky Way, approximately 26,000 light-years away, containing a mass equivalent to roughly 4 million suns. Despite its gargantuan size, this mass is concentrated in a volume smaller than our solar system. While Cygnus X-1 actively consumes material from a nearby companion star, creating intense X-ray emissions visible across vast distances, Sagittarius A star remains relatively quiescent, flaring only when it ingests interstellar gas and dust. Studying both black holes provides invaluable insight into different stages of black hole evolution. Cygnus X-1 represents the final stage of massive stars, whereas Sagittarius A star exemplifies the colossal entities that govern entire galaxies. Their stark contrasts illuminate the rich diversity of black holes, spanning from stellar remnants to galactic titans. Cygnus X-1 shares many fundamental characteristics with other stellar mass black holes in binary systems, having formed from the collapse of a massive star into an ultra-dense object with gravity so extreme that light itself cannot escape. Its immense gravitational pull draws material from its companion star, forming a spiraling accretion disk that emits brilliant X-rays. However, Cygnus X-1 distinguishes itself in several ways. It is one of the nearest known black holes to Earth, located about 6,000 light-years away, making it exceptionally valuable for study. Its mass, estimated at 15 times that of our Sun, places it near the upper end of the stellar mass black hole range. Cygnus X-1's companion star is also remarkable, a blue supergiant, far more massive than typical stars paired with black holes in binary systems. This star provides an abundant material supply, fueling the black hole and contributing to its brightness in X-ray observations. These unique traits make Cygnus X-1 a crucial target for understanding the physics of black holes and their interactions with companion stars, offering a window into the life cycles of massive stars and the extreme environments shaped by their remnants. Cygnus X-1, a stellar mass black hole, differs fundamentally from supermassive black holes at galactic centers. Formed from the collapse of a massive star, Cygnus X-1 is compact, orbiting a blue supergiant star and siphoning material into a luminous accretion disk that renders it one of the brightest X-ray sources in the sky. Supermassive black holes, by contrast, are true cosmic giants, with masses ranging from millions to billions of suns, shaping the evolution of entire galaxies through their gravitational influence. Their formation is still debated, possibly arising from mergers of smaller black holes or the direct collapse of enormous primordial gas clouds. The gravitational influence of these two black hole types varies dramatically. Cygnus X-1 impacts its immediate stellar neighborhood, whereas supermassive black holes control star formation and galactic dynamics on an extraordinary scale, demonstrating the broad spectrum of black hole behavior across the universe. Cygnus X-1 remains a benchmark in astrophysics, offering comparisons with other black holes and refining our understanding of accretion, gravitational effects, and X-ray emissions. By examining its interactions with its companion star, scientists gain critical insights into the mechanics of black holes, enhancing models of their behavior across different scales, and further unraveling the mysteries of these cosmic powerhouses. Furthermore, the spin rate of Cygnus X-1, approaching the theoretical maximum, opens an extraordinary window for testing Einstein's theory of general relativity under conditions that push the limits of physics. By comparing this rapidly rotating black hole to others with slower or differently oriented spins, Scientists can probe how rotation warps the fabric of space-time itself, revealing the subtle yet profound ways gravity bends reality around these cosmic titans. Cygnus X-1 is not merely another black hole, it is a singular entity within the galaxy, distinguished by its extreme rotational velocity, dynamic environment, and the remarkable celestial choreography in which it participates. This stellar mass black hole shares an intimate gravitational dance with a massive blue supergiant star, forming a binary system of rare complexity. The immense gravitational pull of Cygnus X-1 continuously siphons material from its luminous companion, creating a searingly hot accretion disk. Within this spinning whirlpool of superheated gas, matter accelerates to incredible speeds, emitting X-rays of such intensity that Cygnus X-1 ranks among the brightest X-ray sources in our galaxy. But this interaction is not static. The system produces relativistic jets, streams of particles hurtling outward at nearly the speed of light, painting the cosmos with streaks of energy. Unlike isolated black holes, the environment surrounding Cygnus X-1 is in perpetual flux. Winds from the supergiant collide with the accretion disk, sculpting intricate patterns of gas flow, radiation, and turbulence, a living laboratory of cosmic mechanics, where matter under extreme conditions can be studied in real time. At a distance of approximately 6,000 light-years from Earth, Cygnus X-1 is comparatively nearby, allowing astronomers to observe its activity with a clarity rarely afforded for such objects. This proximity has enabled the detection of subtle phenomena, including frame dragging, where the rotating black hole literally twists the space-time around it, and the behavior of matter as it approaches the event horizon, the point of no return. As one of the earliest black hole discoveries, Cygnus X-1 has profoundly shaped the scientific understanding of these enigmatic objects. Its binary configuration, rapid rotation, and massive X-ray emissions make it a veritable cosmic laboratory, providing insights that extend far beyond the system itself. Cygnus X-1 weighs in at an estimated 15 times the mass of our Sun, classifying it as a stellar mass black hole. Its rotation, approaching half the speed of light, distorts the surrounding space-time in ways that reveal the complex interplay of matter and energy in extreme gravitational fields. The X-ray emissions, fluctuating over milliseconds, offer an unprecedented glimpse into the dynamic processes at play near the event horizon. Every pulse of energy, every flicker of radiation, is a message from the edge of physics, a signal from the frontier of our understanding. The study of Cygnus X-1 has confirmed the existence of stellar mass black holes, formed from the catastrophic collapse of massive stars. By observing the orbital behavior of its blue supergiant companion, scientists have measured the black hole's mass, ruling out any other type of celestial object. These findings catalyzed the search for similar binary systems throughout the Milky Way, revealing that stellar mass black holes are far more common than once believed. Techniques developed through decades of study of Cygnus X-1 have been applied to uncover numerous black hole candidates, deepening our comprehension of black hole formation, evolution, and interaction with their surroundings. Cygnus X-1 has also played a critical role in refining models of binary black hole systems, illuminating the ways in which black holes influence their stellar companions, sculpt accretion disks, and drive relativistic jets. These insights extend to intermediate mass and supermassive black holes, connecting the microcosmic behavior of stellar mass black holes with the grand architecture of galaxies across the cosmos. By observing Cygnus X-1, astronomers witness not only the end of a massive star's life, but also the genesis of elements that will seed future star systems, contributing to the cosmic recycling process essential for planets and life. The system's X-ray brilliance, variable on timescales as short as milliseconds, acts as a pulsating beacon of high-energy physics. Each flare encodes the extreme gravitational dynamics occurring just beyond the event horizon, offering a natural laboratory for testing general relativity. By studying the interactions between Cygnus X-1 and its companion, scientists gain critical insights into matter under conditions impossible to replicate on Earth, informing models of cosmic evolution, stellar life cycles, and the violent yet creative processes that shape galaxies. Moreover, Cygnus X-1 provides a window into the early universe. Its formation from the collapse of a massive star offers clues about the first generations of stars that emerged after the Big Bang. These ancient stars, far more massive than most seen today, likely produced the earliest black holes, seeding the cosmos with gravitational anchors that shape the development of galaxies. The continued observation of Cygnus X-1 allows astronomers to connect the physics of the present with the history of the universe, tracing the life cycle of stars, the behavior of matter under extreme forces, and the intricate dance of gravity that governs both stellar and galactic evolution. In every way, Cygnus X-1 embodies a living laboratory of the cosmos, a place where matter, energy, and gravity converge in their most extreme forms. It challenges our understanding, tests our theories, and inspires the ceaseless pursuit of knowledge. Through its dynamic interactions, rapid spin, and intense emissions, it reveals the extraordinary complexity and interconnectedness of the universe, offering a rare glimpse into the forces that govern space, time, and the fabric of reality itself. Furthermore, the staggering X-ray emissions from Cygnus X-1 provide an unparalleled window into the behavior of matter under conditions of extreme gravity, allowing scientists to probe phenomena that cannot be recreated on Earth. These observations offer crucial insights into the laws of physics that governed the universe in its earliest moments, when densities were unimaginably high and temperatures soared far beyond anything we experience today. Cygnus X-1 functions as a natural laboratory, enabling precise tests of general relativity in the most intense gravitational fields, revealing how gravity shaped the infant universe. Through these studies, researchers gain indirect clues about the elusive nature of dark matter and dark energy, the mysterious components that have driven cosmic evolution from the very beginning. Objects like Cygnus X-1, a well-known stellar mass black hole, exert immense influence over the cosmos. Their gravitational pull shapes the distribution of matter and energy over enormous distances, playing a vital role in the large-scale structure of the universe. Often residing at the centers of galaxies, these black holes can grow to supermassive scales. As they consume nearby matter, they unleash colossal amounts of energy in the form of radiation and high-velocity jets. This energy can heat surrounding gas, halting its collapse into new stars in a process known as feedback, which regulates star formation and dictates the evolutionary path of galaxies. On scales beyond individual galaxies, black holes contribute to the formation and stability of galaxy clusters and superclusters. The combined gravity of these black holes, their host galaxies, and the surrounding dark matter halos binds these immense cosmic structures together. The jets emitted by active black holes like Cygnus X-1 extend far beyond their host galaxies, interacting with the intergalactic medium, distributing heavy elements, and sometimes triggering star formation in distant regions. In this way, black holes serve as engines of cosmic recycling, influencing matter and energy distribution across billions of light years. The life cycle of galaxies is intimately linked to the presence and activity of black holes. Supermassive black holes at galactic centers, millions to billions of times more massive than Cygnus X-1, act as cosmic regulators, modulating star formation and galactic dynamics. Matter spiraling into a black hole forms an accretion disk, heating up to extreme temperatures and emitting jets of particles and radiation that can either compress nearby gas to trigger star formation or expel it to suppress stellar birth. When galaxies collide, their central black holes eventually merge, producing gravitational waves and reshaping the galactic landscape, contributing to the evolving cosmic web. Cygnus X-1 also serves as a critical platform for exploring extreme physics. Observing how matter behaves near its event horizon allows scientists to test and refine theories of gravity and probe the fundamental nature of space and time. These investigations enhance our understanding of stellar evolution, the dynamics of extreme gravitational environments, and the formation of black holes themselves. While the connection to dark matter and dark energy is indirect, the study of Cygnus X-1 informs models of how gravity interacts with these unseen components, improving predictions of galactic rotation curves and the expansion of the universe. Cygnus X-1, the first black hole ever confirmed, continues to illuminate our understanding of the universe and even inspires multiverse theories. Its existence underscores the fine-tuned physical constants, such as the strength of gravity and the speed of light, that permit the formation of stars, galaxies, and black holes. This apparent precision fuels hypotheses that our universe is one of many, each with distinct physical laws and potentially dramatically different cosmic structures. Some speculative theories even suggest that black holes like Cygnus X-1 could act as gateways to other universes or dimensions, pushing the boundaries of theoretical physics and challenging our understanding of reality itself. As a powerful X-ray source within our galaxy, Cygnus X-1 remains a vital laboratory for studying the extreme physics of black holes. Its intense gravitational field provides an opportunity to test Einstein's theory of general relativity in regimes impossible to replicate elsewhere. By observing matter and energy interactions near this black hole, scientists refine models of stellar collapse, black hole formation, and galactic evolution. These studies are crucial for predicting the long-term behavior of the universe, offering insights into its potential destiny, whether that entails endless expansion, gradual collapse, or some alternative cosmic conclusion. Cygnus X-1 continues to push the frontiers of astrophysics, shaping our understanding of the universe's most extreme phenomena and offering a profound glimpse into the forces that govern the cosmos.